we are going to discuss another concept. It is the frequency response analysis. So we are going to study the frequency response analysis. Suppose if you take a system, and the system, the input is R of t and the output is C of t. So for the system, the gain is G of S. So for the system, the gain is G of S and the input is R of t and the output is C of t. So this is again G of S. Basically, it is a complex number. We can go for the magnitude as well as the phase angle also we are going to get. So magnitude of G of S and phase angle of G of S. So basically, suppose input R of t is equal to A into sine of omega 1 t plus phi 1 is there. Then what is the output I want to figure out? So basically, the output is nothing but whatever this magnitude value. So at this corresponding frequency, S is equal to J omega 1. So if you substitute S is equal to J omega, and then we are going to get some equation in terms of omega. So if you substitute this omega in this equation, we are going to get some magnitude and phase angle. So this magnitude, we have to multiply for this magnitude, and this phase angle, we have to add here. So therefore, we are going to get A into magnitude of G of S at S is equal to J omega 1 sine of omega 1 t plus phi 1 plus this phase angle G of S at S is equal to J omega 1. So this is the output that you are going to get. So therefore, whenever you are going to give any input, the output will have a magnitude which is equal to this input magnitude into this magnitude value. And the phase angle is nothing but whatever this phase angle, just we have to add this phase angle for this given input, then we are going to get the overall output which is equal to this one. So G of is nothing but it will have some magnitude and say some phase angle. So option S is equal to J omega 1, where omega 1 is the which is the frequency. It is basically associated with the input signal frequency. So now we are going to get the magnitude part and phase angle. So you have to multiply this magnitude for this input magnitude, and you have to add this phase angle for this. In the inward, we have to add this phase angle here. So therefore, we are going to get finally A into magnitude of G of S at S is equal to J omega 1 sine of omega 1 t plus phi 1 plus phase angle of G of S at S is equal to J omega 1. So simply we can say, see, both your signals will have the same frequency. Here the frequency omega 1, here also the frequency is omega 1. So input signal and output signal will have the same frequencies, but only thing is their magnitudes are different and their overall phase angles are different. This is the only difference. So both will have the same frequency, but only thing is they have the different magnitudes as well as the different phase angles. So this is all about this one. Here is sine means here also sine. Here is cos means here also cos. The nature is same, but only thing is the phase angles are different and the magnitudes are different. So the output magnitude is multiplication of the input magnitude with the magnitude of the transfer function, and the output phase angle is the summation of the phase angle of this input plus the phase angle of this transfer function. So therefore we can say finally, if R of t is equal to A into sine of omega 1 t plus phi 1, then C of t is equal to A into magnitude of G of S at S is equal to J omega 1 into sine of omega 1 t plus phi 1 plus phase angle of G of S at S is equal to J omega 1. So this is all about this one. So this is what the frequency response analysis means. If you are going to give input as a sine or cos, then what is the nature of the output? C of t. If sine is sine, cos means cos. Only their magnitudes are changed and the phase angles are changed. Even everything is same, like frequency is same. Sine means sine, cos means cos. So this is about the frequency response analysis. So now we will discuss something more, which is the frequency response analysis of the second order system. So we are going to learn about the frequency response analysis of the second order system. So what is the frequency response analysis of the second order system? We are going to study in a very detailed manner. So what is the frequency response analysis of the second order system? So you can see clearly what is the transfer function of a standard second order system. So you know we can see the transfer function of the standard second order. We can say, I already told you what the transfer function of the standard second order system, which is omega n square by s square plus 2 zeta omega ns plus omega n square. So this one I have already told you. So this is called as the transfer function of the standard second order system, which is C of s by R of s is equal to omega n square by s square plus 2 zeta omega ns plus omega n square. So simply we are going to call this as the m of s. So we are going to call this as the m of s. So if you substitute s is equal to j omega, and if you try to get the magnitude part, so basically if you substitute s is equal to j omega, we are going to get the complex part as well as the real part. So I want to take out the magnitude part. So if we substitute the magnitude part, we are going to get like this, which is 1 by under root over 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square. So this is what you are going to get. Listen carefully. The amount of the m of j omega is equal to 1 by under root over 1 minus omega by omega n whole square. So this is square is there. Again whole square plus 2 into zeta into omega by omega n whole square. So this is a point always you have to keep in your mind. The amount of m of j omega is equal to 1 by under root over 1 minus omega by omega n. Here there is a square. So square again whole square plus 2 zeta omega by omega n whole square. So therefore the amount of m of j omega is equal to 1 by under root over 1 minus omega by omega n whole square again whole square plus 2 zeta omega by omega n whole square. So now I want to know what is the magnitude of this transfer function with respect to omega. So then I want to find what is the value. Suppose if you substitute omega is equal to 0, then what you are going to get? So this part is equal to 0, this part is equal to 0. Only 1 is going to remain. So 1 by root over 1 is equal to 1 you are going to get. That is the reason its value is equal to 1. And that is the reason its value is equal to 1 you are going to get. So here you are going to get its value is equal to 1. So in this format you are going to get here. So you can see clearly from this picture, we can see like this you are going to get. So if you substitute omega is equal to 0, we are going to get its value is equal to 1 because this part is equal to 0, this part is equal to 0, this part is equal to 0. So only 1 is going to remain. So you are going to get its value is equal to 1. See, as the omega increases, the denominator is going to get increased. So overall value is going to get decreased. So that is the reason this value is going to increase for a small amount of time and finally is going to get decreased. So this is the nature that we are going to see here. So this is called as a resonant peak. So this is called as a resonant peak. So this is called as a resonant peak MR. This is called as a resonant peak and this is called as a resonant frequency. And this is called as the cutoff frequency of bandwidth. Cutoff frequency of bandwidth. This is called the cutoff frequency of bandwidth. So you can see. So this is called as the resonant peak and this is called the resonant frequency and this is called as a cutoff frequency of bandwidth. So now we'll discuss these values. See, what is the meaning of resonant frequency? It is a frequency at which this magnitude value will have the highest value, it will have the peak value. So therefore, this peak is going to occur at a certain frequency that is called as the resonant frequency and this peak value is the resonant peak. So therefore, this magnitude of m of j omega is going to at a particular frequency to have the peak value that is called as the resonant frequency and this peak value is called the resonant and because you can see this is called the resonant frequency and this is the resonant peak. So what is omega value? Omega is equal to omega n into root over 1 minus 2 zeta square. So omega is equal to omega n into root over 1 minus 2 zeta square and the value of zeta should be always less than 1 by root 2. So the value of zeta should be always less than 1 by root 2 which is equal to 0.707. So what is the resonant peak? I have already told you. So if you substitute this frequency, if you substitute the value of omega is equal to omega r and if you simplify, we are going to get the peak value which is equal to 1 by 2 zeta and root over 1 minus zeta square. So you simply see if you do the derivative of this one with respect to omega and it will equal to 0, then what you are going to get? You are going to get the frequency at which this is going to have a peak value. So that frequency is called resonant frequency. And at this omega, you are going to get the peak value. So if you substitute omega is equal to omega, and if you simplify, we are going to get the magnitude value, which is the resonant peak, which is equal to 1 by 2 zeta and root over 1 minus zeta square. So this one always you have to keep in your mind. So therefore, the resonant frequency is equal to omega n into under root over 1 minus 2 zeta square, and the resonant peak is equal to 1 by 2 zeta and root over 1 minus zeta square. So these two formulas always you have to keep in your mind. So we can say that the resonant frequency is equal to omega n into under root over 1 minus 2 zeta square and the resonant peak is equal to 1 by 2 zeta under root over 1 minus zeta square. So these two formulas always you have to keep in your mind. So therefore we can say the resonant frequency is equal to omega n into under root over 1 minus 2 zeta square and the resonant peak is equal to 1 by 2 zeta under root over 1 minus zeta square. So now this question always you have to keep in your mind. Whenever the zeta value is lesser than 0.707 is 1 by root 2. Then the resonant peak is greater than 1. Suppose if zeta is equal to 0.707, then the resonant peak is equal to 1. If zeta is greater than 0.707, then the resonant peak won't exist, means it won't occur. So this is the thing always you have to keep in your mind. So this is the condition always you have to keep in your mind. So whenever zeta value is less than 1 by root 2 or 0.707, then the resonant peak is always greater than 1. If it is equal to 1 by root 2, then the resonant peak is always equal to 1. And if it is greater than 0.707, then the resonant peak won't exist. So this is a beautiful formula always you have to keep in your mind. So therefore we can say whenever the zeta is less than 0.707, then the resonant peak is greater than 1. If the zeta is equal to 0.707, then the resonant peak is equal to 1. And if zeta is greater than 0.707, then the resonant peak won't exist. So this is the beautiful formula always you have to keep in your mind. So therefore we can say that omega r is equal to omega n into under root over 1 minus 2 zeta square. So resonant peak is equal to 1 by 2 zeta under root over 1 minus zeta square. So if you see clearly, this equation is going to satisfy only when zeta is less than 1 by root 2. Suppose if it is greater than 1 by root 2, then what is going to happen? Then this resonant peak won't even exist because this value will become negative. Negative means under root over minus 1 is j complex. So it won't exist. So that is the reason this equation is going to get hold only when zeta is less than 1 by root 2. Suppose it is greater than 1 by root 2, then definitely this value will become negative. So therefore the negative frequency won't exist. So therefore this equation is going to be valid only for zeta less than 1 by root 2. So therefore we can say simply whenever the zeta value is less than 1 by root 2, then the resonant peak is always greater than 1. Whereas we can say if the zeta is equal to 0.707 or 1 by root 2, then the resonant peak is equal to 1. And if the zeta is greater than 0.707, then the resonant peak won't even exist. So this one always you have to keep in your mind. So now what is the bandwidth? So what is the bandwidth means? We can say, so bandwidth means basically we can say it is a frequency at which its value will become 1 by root 2 times the initial value. It will become 1 by root 2 times the initial value. So this is the frequency at which, so we can say omega c is nothing but it is a cutoff frequency or the bandwidth at which we can say the magnitude of this transfer function will become 1 by root 2 times the initial value, which is 1 by root 2 times the initial value is 1. So you are going to get 1 by root 2. So this is the frequency at which this value will become 1 by root 2. So if you substitute at omega is equal to omega c, its value is equal to 1 by root 2. So if you substitute and simplify, we are going to get the cutoff frequency of the bandwidth is equal to omega n into under root over 1 minus 2 zeta square plus under root over 4 into zeta to the power of 4 minus 4 zeta square plus 2 radians per second. So this is the same as the previous one, but extra factor we have to add 4 into zeta to the power of 4 minus 4 zeta square plus 2 radians per second. So it is nearly equal to, so this is a very complex set. So we can simplify to a very simple equation which is nearly equal to omega n into minus 1.19 zeta plus 1.85 radians per second, and it is also nearly equal to 2 into zeta into omega n. So this is the way we can write. So this is the exact expression. These are the both approximate expressions. These are the approximate expressions. So these are the approximate expressions. So always remember bandwidth is equal to omega c is equal to omega n into under root over 1 minus 2 zeta square plus under root over 4 into zeta to the power of 4 minus 4 zeta square plus 2 radians per second. So this is the actual expression, but if you want the approximate expression, it is nearly equal to omega n into minus 1.19 zeta plus 1.85 radians per second, and is also nearly equal to 2 into zeta into omega n. So this is the exact expression, and these two are the approximate expressions. So these things always you have to keep in your mind. So we can say bandwidth is equal to omega c is equal to omega n into under root over 1 minus 2 zeta square plus under root over 4 into zeta to the power of 4 minus 4 zeta square plus 2 radians per second, and is nearly equal to omega n into minus 1.19 zeta plus 1.85 radians per second, and is nearly equal to 2 into zeta into omega n. So these formulas always you have to keep in your mind. So finally I can say the bandwidth is equal to omega c is equal to omega n into under root over 1 minus 2 zeta square plus under root over 4 into zeta to the power of 4 minus 4 zeta square plus 2 radians per second, and it's approximately equal to omega n into minus 1.19 zeta plus 1.85 radians per second, and is still nearly equal to 2 into zeta into omega n. So this is all about this one. Suppose if you are going to draw the Bode plot of this one, if you are going to plot the Bode plot of this one, and what you are going to get? The mounted Bode plot we are going to draw, then what you are going to get? Like this you are going to get. So you can see 20 into log base 10 mod of m of j omega. So 20 into log mod of m of j omega with the base 10. So if you are going to draw, you are going to get in this format. So you can see this is a pole of order 2, means we are going to get minus 4 decibels per decade. So minus 4 decibels per decade, it is going to occur at omega is equal to omega n. Omega is equal to omega n. So this is a minus 4 decibels per decade. Up to this one, it will be 0. So this is called as the asymptotic plot or approximated plot. But the actual plot is like this. So this is the actual plot you are going to get. So this is the actual plot, and this is the asymptotic plot. So at omega is equal to omega n, the slope is going to start with minus 1 decibels per decade. So then what is the value of this x? X is nothing but minus 20 log 2 zeta. So this x is equal to minus 20 log 2 zeta. So this is the exact, or we can say actual plot. So x is equal to minus 20 log 2 zeta. I've already told you what is the NP. NP is called the resonant peak, and omega is called as a resonant frequency. Whereas MR is called as a, see, this is NP is called resonant. So basically we can say here MR, not NP. So this is MR. MR is called as a resonant peak, and omega is called resonant frequency. Small correction here. This is not P, this is MR. MR is resonant peak, and the omega is called the resonant frequency. So omega is called the resonant frequency, and MR is called the resonant peak. So we can say MR is called the resonant peak, and omega is called the resonant frequency. So this is the Bode plot, the magnitude Bode plot of this transfer function. So basically it is a pole of 2 order. So you are going to get minus 1 decibels per decade, and it is going to occur at omega is equal to omega n. It is going to get occur until that time with 0 dB, here minus 1 decibels per decade. So this is the approximated or asymptotic plot or approximated plot, and this is the actual plot, and its value is x is equal to minus 20 log 2 zeta, minus 20 log 2 zeta. So MR is called the resonant peak, and omega is called the resonant frequency. So these things always you have to keep in your mind. So this is all about the analysis of the frequency response analysis of the standard second order system. So now we are going to discuss some more important points, which is gain crossover frequency. So gain crossover frequency means the notation is omega JC. So this is called as the gain crossover frequency. So we can say that this is a frequency at which the amount of the open loop transfer function is equal to 1. So gain crossover frequency is defined as it is a frequency at which the amount of the open loop transfer function is equal to 1. It is amount of J of S, H of S at omega is equal to omega GC. We are going to get its value is equal to 1. Then what is the value of 20 log 10 amount of J of J omega, H of J omega at omega GC, which is equal to, you can say 0 dB. So you can see clearly from this picture, this is the value is equal to, at omega GC its value is equal to 0 dB. So here you can see clearly here. Therefore we can say finally that gain crossover frequency means it is a frequency at which the amount of the open loop transfer function is always equal to 1. So therefore the 20 log base 10 with the pod of G of J omega, H of J omega at omega GC is nothing but it is equal to 0 dB. So we can say what is the meaning of gain crossover frequency? It is a frequency at which the amount of the open loop transfer function is equal to 1. So therefore the amount of J of S, H of S at omega is equal to omega GC, we are going to get its value is equal to 1. Then 20 log base 10 mod of J of S, H of S at omega is equal to omega GC, its value is equal to 0 dB because this magnitude is equal to 1. So 20 log 10 base 10 is nothing but it is equal to 0. This is basically 0 dB. Now what is the meaning of phase crossover frequency? Phase crossover frequency notation is omega PC. So it is a frequency at which the phase angle of the open loop transfer function is equal to minus 180 degree. So it is a frequency at which the phase angle of the it is a frequency at which the phase angle of the open loop transfer function is equal to minus 180 degree. So therefore the phase angle of G of S, H of S and omega PC, its value is equal to minus 180 degree. So these things always you have to keep in your mind. So therefore we can say the phase crossover frequency means it is a frequency at which the phase angle of the open loop transfer function is equal to minus 180 degree, which is phase angle of g of h of s and omega PC is equal to minus 180 degree. Then what is gain margin? Gain margin is Cm. So gain margin is the reciprocal of the magnitude of the open loop transfer function at omega PC. So you can say gain margin is equal to 1 by magnitude of open loop transfer function at omega PC. So here G means here use P, phase crossover frequency. So we can say the gain margin is the reciprocal of the magnitude of the open loop transfer function at the phase crossover frequency. Then, so this is basically unitless. It is a unitless. Suppose if we want to mention the gain margin in dB, then 20 log gas margin with a base 10 is equal to. So if you use this here, the gain margin is equal to this value. You substitute here, and if you simplify, we are going to get finally minus 20 log of mod of g of j omega h of j omega at omega PC with a base 10. And then this is basically unitless, and this is the having gain out of dB. So here, suppose in the question if they are asking the gain margin in unitless means use this formula. If they are asking in terms of dB means use this formula. Then what is this formula you have to remember, which is the magnitude of the open loop transfer function. See, magnitude of g of s h of s at omega PC is equal to, it is a ratio of the k divided by k margin. So this is also one more important formula you have to remember. So even though if you forget this also, still you can get the result. So therefore we can say the magnitude of g of s h of s at omega PC is equal to the k divided by k marginal. So you know in ABCD, D is going to come earlier than M. So use the D, then come to M. So it is a ratio of the K divided by K marginal. Then what is the phase margin? Phase margin means we can say what is the phase margin? Phase margin formula we have to remember. The phase margin is equal to, always you have to remember, which is the phase margin is equal to 180 degree plus the phase angle of G of S, H of S at omega GC. So here phase margin means here P means here use G. Gain margin means I have already told you it is equal to 1 by magnitude of G of S, H of S at basically you can say at omega PC. So vice versa. Here P means here G means here P. Vice versa you have to remember. So here P means here use G, here G means here use P. So these things always you have to keep in your mind. So what is the phase margin? Phase margin is equal to 180 degree plus the phase angle of G of H of S at omega GC. Whereas the gain margin is the 1 by magnitude of G of H of S at omega PC. So these things always you have to keep in your mind. So these are the important, these things always you have to keep in your mind. So finally I can say gain crossover frequency means it is a frequency at which the magnitude of the open loop transfer function is equal to 1. And phase crossover frequency is a frequency at which the phase angle of the open loop transfer function is equal to minus 180 degree. And the gain margin is equal to 1 by magnitude of the open loop transfer function at phase crossover frequency, whereas the phase margin is equal to 180 degree plus the phase angle of the open loop transfer function at gain crossover frequency. So these things always you have to keep in your mind. So now we'll discuss some important points. So for a stable system, always the gain margin and the phase margin are positive. Gain margin is positive means in terms of dB. So this is in terms of dB only they are saying. So this is gas margin is basically in terms of dB and the phase margin in terms of degrees. So we can say the gain margin in terms of dB is positive and the phase margin is also positive. So we can say here the gain crossover frequency is always lesser than the phase crossover frequency. Whereas for the marginal stable system, the gain margin is equal to 0 dB and the phase margin is equal to 0 degree. So always the gain crossover frequency is equal to phase crossover frequency. Whereas in the case of unstable system, the gain margin is equal to negative and the phase margin is also equal to negative. So we can say the gain crossover frequency is greater than the phase crossover frequency. So these things always you have to keep in mind. So we can say for the stable system, gain margin is equal to positive and the phase margin is equal to positive and the gain crossover frequency is lesser than the phase crossover frequency. Whereas in the case of marginal stable system, the gain margin is equal to 0 dB and the phase margin is equal to 0 degree and the gain crossover frequency is equal to phase crossover frequency. Whereas in the case of the unstable system, the gain margin is equal to negative dB and the phase margin is equal to negative degrees So therefore, the gain crossover frequency is always greater than the phase crossover frequencies. So this one always you have to keep in your mind. So therefore, finally I can say for a stable system, gain margin is a positive and the phase margin is positive, and the gain crossover frequency is always lesser than the phase crossover frequency. So G is going to come earlier than P. A, B, C, D, E, F, G. So therefore, G is going to come earlier than P. So use here lesser is equal to and greater. Shortcut to remember. So here lesser, here equal, here greater. So G is going to come earlier than P. Omega G is and omega P C. So here lesser, here equal, here greater. So for a stable system, the gain margin is G positive and the phase margin is also positive. And the gain crossover frequency is always lesser than the phase crossover frequency. Whereas for the marginally stable system, the gain margin is equal to 0 as well as the phase margin is equal to 0, and the gain crossover frequency is always equal to phase crossover frequency. Whereas for the unstable system, the gain margin is equal to negative as well as the phase margin is also equal to negative, and the gain crossover frequency is always greater than the phase the gain crossover frequency is always greater than the phase crossover frequency. So this point I wanted to only show a number of times. So this data always you have to keep in your mind. So now we are going to discuss another concept, which is the gain margin and the phase margin for the second order systems. So we are going to calculate the gain margin as well as the phase margin for the second order systems. So this is the thing that we are going to do. So basically for the second order systems, we are going to figure out the gain margin as well as the phase margin. So for the standard second order, the transfer function is C of S by R of S is equal to omega n square by S square plus 2 zeta omega n S plus omega n square. So here there is a S here. So here omega n square by S square plus 2 zeta omega n S plus omega n square. So small correction here. So therefore this is the standard transfer function of a second order system, which is C of S by R of S is equal to omega n square by S square plus 2 zeta omega n S plus omega n square. So now this one, basically we are going to assume G of S is equal to omega n square by S into S plus 2 zeta omega n, whereas H of S is equal to 1. So you can see clearly in the block diagram. So this is the for negative feedback system of unity feedback, H of S is equal to 1 and G of S is equal to omega n square by S into S plus 2 zeta omega n. Then what is the the transfer function, which is C of S by R of S is equal to G of S by 1 plus G of S H of S. So G of S, H of S, just substitute simplify. We are going to get this equation, which is C of S by R of S is equal to omega n square by S square plus 2 zeta omega n S plus omega n square. So now we got the value of G of S and we got the value of H of S. So now I am going to just replace S by J omega. Then I am going to get G of J omega is equal to, because G of S into H of S is again equal to G of S only. So therefore G of S into H of S is again this value itself. So therefore here I am going to write here for an easy purpose. So that here I will write here H of J omega also I am going to write here. So therefore we can say G of J omega into H of J omega, which is equal to omega n square by we can say S into S plus 2 zeta omega n. So in place of S I have replaced J omega, then I am going to get, which is omega n square by minus omega square plus 2 zeta omega n into omega into J. So basically it is having a real part as well as the imaginary part. So I will get only the magnitude part, which is omega n square by under root over, you can say omega square whole square plus 2 zeta omega n omega whole square, and the phase angle is. So if you see clearly, this is so the down part is basically, you can see clearly this is a negative and this is a positive. So this is the angle that you are going to get. So what is this overall angle? It is equal to 180 minus tan inverse of 2 zeta omega n omega by omega square. So this is basically 180 minus, but if it go upward it will become reverse. So minus 180 plus tan inverse of 2 zeta omega n omega by omega square. So if we simplify, we are going to get finally, which is omega n square by under root over omega to the power of 4 plus 2 zeta omega n omega whole square at an angle of minus 5 degree plus tan inverse of 2 zeta omega n by omega. So this is what we are going to get. So basically, this downward I have taken the magnitude and the phase angle. The downward phase angle is so here negative, here positive. So therefore 180 minus tan inverse of 2 zeta omega n omega by omega square. So if it go to the upper part, it will become reverse. So minus 180 plus tan inverse of 2 zeta omega n omega by omega square. So if we simplify, we are going to get this is the magnitude and this is the phase angle that we are going to get. So now, basically, what is the phase crossover frequency? Phase crossover frequency is the frequency at which the phase angle of the g of j omega into h of j omega is equal to minus 180 degree. So this one I already told you. Therefore, we can say that phase crossover frequency is the frequency at which the phase angle of g of s h of s is equal to minus 180 degree. So now, I will at this frequency, I will try to equate this part to minus 180 degree. Then what is going to happen? If this is minus 180, so minus 180 minus 180 cancels, then we are going to get tan inverse of 2 zeta omega n by omega is equal to 0. So therefore, we are going to get tan inverse 0 is nothing but tan 0. Tan 0 is equal to 0. So therefore, what we are going to get finally, so therefore, see, tan inverse of this part is equal to 0, you are going to get, so tan 0 is nothing but 0 degree. So therefore, we can say, finally, you are going to get 2 zeta omega n by omega, you are going to get its value is equal to 0. So if this value is equal to 0, means we can say, what is the value of omega PC? This omega PC is going to become, so omega PC is equal to infinity because these are some non-zero values. So therefore, this must become infinity. Whenever this overall value will become 0. So this value is equal to infinity. So phase crossover frequency is equal to infinity. But the standard second order equation. Understand? Standard second order systems. And what is the gain margin? So gain margin, gain margin is nothing but, which is the gain margin is equal to 1 by mod of g of s h of s at omega PC. So what is the value of omega PC? So basically this is the magnitude part, right? So if substitute omega PC, what is the magnitude we are going to get? So this is omega n square by under to the power of 4 by 2 zeta, here omega n omega whole square. So in place of omega, I am substitute the omega PC. So definitely this part is infinite. So anything by infinity is nothing but 0. So this magnitude part we are going to get 0. So this magnitude part is 0 means 1 by 0 is nothing but which is equal to infinity. So therefore we can say the gain margin is equal to infinity and the phase crossover frequency is also equal to infinity. Now let's go for the gain crossover frequency. Gain crossover frequency means it's the frequency at which the amount of the g of s into h of s is equal to 1. So gain crossover frequency is the frequency at which the amount of g of s h of s is equal to 1. So g of s h of s, the magnitude part is equal to 1 means this will need to be equal to 1. So at a gain crossover frequency means replace omega by omega gc. So if you equate this part to 1, so if we equate this part to 1, so this magnitude part equal to 1 at omega gc. So if we simplify, we are going to get the gain crossover frequency is equal to under root over minus 2 zeta square omega n square plus omega n square under root over 4 into zeta to the power of 4 plus 1 radians per second. So this is the frequency at which the magnitude of the g of h of s is equal to 1. So this is a gain crossover frequency, which is equal to under root over minus 2 zeta square omega n square plus omega n square under root over 4 into zeta to the power of 4 plus 1 radians per second. So now let's go for the phase margin. So phase margin formula which is 180 degree plus the phase angle of g of h of s at omega gc. So now basically this is 180 plus. So what is the phase angle? So this is a phase angle at omega g. So you always have the idea g of s at h of j omega. Always you have the idea. So therefore you can say that. So this part. So this part which is minus 180 degree plus tan inverse of. In place of omega, I need to substitute. In place of omega, I need to substitute omega gc. Omega gc. So you are going to get 2 zeta omega n by omega gc. So the value of omega gc. So the value of omega gc. So therefore, if you take omega n square common, common, then what you are going to get? You are going to get in this format, right? So if you take omega n common, then you are going to get omega n square. If you take outside, it will become omega n under root over minus 2 zeta square plus under root over 4 into zeta to the power of 4 plus 4. So this is what you are going to get, right? Omega gc. Same thing, I have substitute in place of omega, I have substitute omega gc. Then this omega n cancels. Finally, you are going to get 2 zeta by under root over minus 2 zeta square plus under root over 4 zeta to the power of 4 plus 1. Same thing, everything. So this omega n cancels. And then you are going to get in this format. So this plus 180 and minus 180, we are going to get cancelled. And finally, we are going to get tan inverse of 2 zeta by under root over minus 2 zeta square plus under root over 4 into 3 to the power of 4 plus 1. So this is what we are going to get, a phase margin. So this is the angle that we are going to get, tan inverse of 2 zeta by under root over 1 is 2 zeta square plus under root over 4 into raised to the power of 4 plus 1 in terms of degrees. This is a very complex expression. It is approximately equal to r into zeta. So this equation is going to hold only for zeta less than 1 by root 2. So this approximation is going to hold only for zeta less than 1 by root 2. So this one always you have to keep in mind. So but this is the actual expression. So this is the actual expression, but the approximate expression is nearly equal to r into zeta for zeta less than 1 by root 2. So this approximation is going to hold only for zeta less than 1 by root 2. So now basically we can write this one in the other format also. So we can write in this one in the other format also, which is 90 degree minus tan inverse of reciprocal of this one, which is under root over minus 2 zeta square plus under root over 4 into 10 to the power of 4 plus 1 by 2 zeta. So like this also you can write. Either this is correct or either this is also correct. 90 minus tan inverse of under root over minus 2 zeta square plus under root over 4 into 10 to the power of 4 plus 1 by 2 zeta. So both are correct. Either you can write in this format or either in this format also, and your both are correct. Sure. But this is an exact expression. If you want to write in the other format, so use a 90 degree minus tan inverse of, do the reciprocal of this one. So and here everything is correct. So this is the exact expression. This is also exact expression, and this is the approximate expression, which is nearly equal to 100 zeta for zeta less than 1 by root 2. So this approximation is going to hold only for zeta less than 1 by root 2 only, but not above this one. So I've already told you the unit of the phase margin is always in terms of degree. So it's the same thing I have written. So therefore I've already told you this is a basic block diagram of this system. G of n is equal to omega n square by s into s plus 2 zeta omega n, and h of s is equal to 1. So therefore finally I can say for the standard secular system, we got the phase crossover frequency is equal to infinity, and we can say the gain margin is equal to infinity, and the gain crossover frequency is equal to, so the simplified expression we have got, which is omega n into under root over minus 2 zeta square plus under root over 4 zeta to the power of 4 plus 1. So this is a simplified expression. Then what is the phase margin? Phase margin exact expression is tan inverse of 2 zeta by under root over minus 2 zeta square plus under root over 4 into zeta to the power of 4 plus 1, or 90 degree minus tan inverse of under root over minus 2 zeta square plus under root over 4 into zeta to the power of 4 plus 1 by 2 zeta, or the approximate expression is 100 zeta. It is going to hold only for zeta less than 1 by root 2 only. So this approximation is going to hold only for zeta less than 1 by root 2 only, and the unit of the phase margin is always in terms of degree. So these are the some of the facts regarding the second order system for the gain margin and the phase margin. Now we are going to discuss another concept, which is the effect of the time delay or the dead time on stability. So what is the effect of the time delay or the dead time on the stability? So we are going to discuss what is the effect of the time delay or the dead time on the stability. So what is the basic time delay of dead time? Means even though input is equal to non-zero, but still output is equal to 0 for small amount of time, that is called as the time delay or the dead time. Listen carefully. When the input is equal to 0, the output is also, see, when the input is not equal to 0, still the output is equal to 0 for small amount of time, that is called as the time delay or the dead time. So therefore we can say even the input is not equal to 0, but the output is equal to 0 for a small amount of time, that is called as the dead time or the time delay. So output is basically the delay of the input. So therefore we can say what is the basically the effect of the time delay or dead time on the stability. This concept we are going to see. So omega GC remains same in both the cases, that is with and without of time delay, but omega PC will decreases. So omega GC, the gain crossover frequency remains same in both the cases, that is with and without the time delay, but the phase crossover frequency is going to get decreases. And the gain margin and the phase margin reduces by addition of the time delay in a system, so stability is going to get decreases. So what is going to happen? Basically, so listen carefully. This is without time delay, and this is with the time delay. So what is going to happen? We are going to see. So the omega GC remains same in both the cases, that is with and without of time delay. So omega GC is equal to constant. So we can say it is a, here it is the same, here also it is same. So it is same in both the cases. It is shown in, it is same in both the cases. Whereas so omega PC decreases. So basically we can say, so when you compare here omega PC is somewhat higher, it is somewhat lesser. So with the time delay, the omega PC is going to get, so it is going to decreases here. So with time delay, the omega PC is going to get decreased when compared with the time delay. And the gain margin, the phase margin reduces by addition of time delay in the system, so stability decreases. So you can say, if you go for the gain margin, so here the gain margin is going to get decreased. So gain margin is going to get decreased here when compared to here. And also phase margin is also going to get decreases. So therefore we can say the stability, what is going to happen? The stability is going to also going to get decreases. So these are the points always you have to keep in your mind. So without time delay and with time delay in the circuit, we can say omega GC is going to remain constant in both the cases, and the phase crossover frequency is going to get decreases, and the gain margin is also going to get decreases, and the phase margin is also going to get reduces, and the stability is also going to get reduces. So these are the effects that you can see in the case of with the time delay. So with the time delay. So these things always you have to keep in your mind. So let me draw this picture somewhat easier so that we can easily able to understand. So this is what we are going to understand. So here I am going to draw the table so that we can easily able to understand. So this is the, I always basically try to make things simplified. That is the reason I teach very slowly. So you can see clearly here. So this is the table. So this is the table. So this is the table I can see in here. So with the time delay, what are the things that are going to happen? So let me show you with a small amount of picture. So this is the omega PC, and this is GM, and this is phase margin, and this is the stability. So this, let me draw here. So this is the picture. So now let me remove this part so that we can easily able to see the picture what I am trying to tell you. So therefore we can say with the time delay, what is going to happen? The omega GC is constant, without time delay and with time delay in the circuit. Whereas the phase crossover frequency is going to get decreases, the gain margin is going to get decreases, and the phase margin is going to get decreases, and the stability is going to get decreases. See, everything is going to decrease except in omega GC. Omega GC is going to remain same in both the cases. So this is the point always you have to keep in mind. So therefore, I can say, and simply, finally I can say that whenever a time delay or the dead time is included in a circuit, then what are the changes that we can see, which is the gain crossover frequencies remain same in both the cases, which is without time delay and with time delay. Whereas the phase crossover frequency is going to get decreases, the gain margin is going to get decreases, and the phase margin is going to get decreases, and the stability is also going to get decreases. So these are the things that you can see here. So finally I can say, by introduction of the time delay circuit, in the control system, the gain crossover frequency is going to remain same, whereas the phase crossover frequency is going to get decreases, and the gain margin is going to get decreases, and the phase margin is going to get decreases, and the stability is also going to get decreases. So these things always you have to keep in your mind. So now, get frequency response analysis of the dead time. So we are going to do some frequency response analysis of the dead time. We are going to do in a very detailed manner. So the frequency response analysis of the dead time. As I already told you, what is the meaning of dead time? Even the input is not equal to 0, but the still output is equal to 0 for a small amount of time, then we can say that system is said to be, that is called the dead time. So output is basically the delay of the input. So y of t is equal to x of t minus capital T. So you can say output is the delay of the input, which is y of t is equal to x of t minus t. Then if you apply the Laplace transform both sides, then we are going to get y of s is equal to e to the power of minus ts into x of s, because basically I've already told you for f of t minus a, the Laplace transform is e to the power of minus ts into f of s. So this formula is already told you. So f of t minus a is Laplace transform e to the power of minus as into f of s. So based on this formula, we can say finally we are going to get y of s is equal to e to the power of minus ts into x of s. So the transfer function is y of s by x of s is equal to e to the power of minus ts. So this is called the transfer function. So I am going to represent by a symbol, which is f of s. So f of s is equal to e to the power of minus ts. But I want to substitute s is equal to j omega. So therefore we are going to get f of j omega is equal to e to the power of minus j omega t. So the another basic formula, e to the power of j theta. E to the power of j theta is equal to cos theta plus j sin theta. So based on this formula, we can say e to the power of j, theta is minus omega t. So cos of minus omega t plus j of sin minus omega t. So cos of minus theta is equal to cos theta. Sin of minus theta is equal to minus sin theta. So based on this, we can say cos of omega t minus j sin omega t. So now this is basically a complex number. It has a real part as well as the imaginary part. So we want to, this is a rectangular format. So I want to convert into magnitude and the phase angle. Therefore, f of j omega is equal to magnitude of the f of j omega, the phase angle of f of j omega. So what is the magnitude? Magnitude is nothing but root over cos omega t whole square plus sin omega t whole square, which is equal to 1, because cos theta plus sin theta is equal to 1. So root over 1 is equal to 1. And what is the phase angle? Phase angle is equal to, here basically you can see the real part is positive and the imaginary part is negative. So means we are going to get like this. So the real part is positive and the imaginary part is negative, means this is angle. So this angle is negative. So basically this angle is negative. So phi is equal to, you can say phi is equal to tan inverse of sin omega t by cos omega t. So basically the angle is negative. So you can say minus tan inverse. So minus tan inverse of sin omega t by cos omega t means we can say tan omega t. So then tan inverse of tan theta is equal to theta. You are going to get tan inverse of tan is something but theta. We are going to get minus omega t. We are going to get same to minus omega t. We are going to get. So this is in terms of radians. So this is in terms of radians because we can see phi is negative. So phi is equal to minus tan inverse of sin omega t by cos omega t. Sin omega t by cos omega t is equal to tan omega t. So you can say minus sin inverse of tan omega t is minus omega t. So you are going to get minus omega t radians. This is in terms of radians. And the magnitude is 1 and in terms of radians is minus omega t. Then we can see clearly here. So therefore we can say for e to the power of minus j omega t, we are going to represent the magnitude part is 1 and the phase angle is minus omega t because e to the power of j theta. So for we can simply write for e to the power of j theta, the magnitude is 1 and the angle is theta. Same thing. So the magnitude is 1 and the angle is theta. In the same fashion, the magnitude is 1, the theta is minus omega t in terms of radians. So if you want to convert this radians into degrees, then what the things that we have to do? So pi radians is equal to 180 degree. Then minus omega t radians I want to know. What is the corresponding degree I want to know? So pi radians means 180 degree. So minus omega t radians I want to convert in terms of degree. So I am going to assume it is equal to x degree. I am going to assume. So do the ratio. Therefore, we can say pi by minus omega t is equal to 180 by x. So if we simplify, we are going to get the value of x, which is equal to minus omega t by pi into 180. So pi value is nothing but so pi is nothing but 3.14. So if we simplify, we are going to get the value is equal to minus 57.3 omega t in terms of degrees because pi is equal to 3.14. So if we simplify, we are going to get in terms of minus 57.3 omega t degrees. So therefore now we can say minus omega t in terms of radians and minus 57.3 omega t in terms of degrees. So this is the way that we are going to represent. So therefore finally I can say e to the power of minus j omega t means the magnitude is 1 and the angle is minus omega t in terms of radians. And if you want to convert in terms of degrees, then we are going to get an angle of minus 57.3 omega t degrees. So these things always you have to keep in your mind. So this is we can say this is simplification always you have to keep in your mind. So whenever in the question they are going to include the delay time, then definitely you have to remember this concept like a fraction of second. Then we can get all the things in a very simple manner. We are going to discuss another concept, which is the polar plot. So polar plot means here drawing the magnitude of the g of s h of s versus the phase angle of g of s h of s when the value of omega is varying from 0 to infinity. So basically, it is a drawing the graph between the magnitude of g of j omega h of j omega versus the phase angle of g of j omega h of j omega when the value of omega is varying from 0 to infinity. That is called as a polar plot. So listen carefully that we are going to draw the graph between the magnitude of the g of s h of s versus the phase angle of g of s h of s when the value of omega is varying from 0 to infinity. This is called as the polar plot. Which we can say it is a graph between the magnitude and the phase angle of the open loop transfer function when the value of the omega is varying from 0 to infinity. So this is a basic concept of the polar plot. Means we are going to draw the graph of the open loop transfer function magnitude versus the phase angle when the value of the omega is varying from 0 to infinity. So this is all about the polar plot. So we can say finally, if you are going to draw the graph of the open loop transfer function magnitude versus phase angle when the value of omega is varying from 0 to infinity, that is called as the polar plot. This is the magnitude of g of j omega h of j omega versus the phase angle of g of j omega h of j omega when the value of omega is varying from 0 to infinity, then we can say that is said to be polar plot. So now we will discuss some important things here. The other concept is the open loop transfer function as well as the polar plot. So we are going to discuss the different types of open loop transfer functions as well as the polar plot we are going to draw in a systematic manner we are going to draw. So listen carefully. Open loop transfer function is g of s h of s. So open loop transfer function we are going to discuss and the corresponding polar plot also we are going to discuss. So listen carefully. Suppose if the open loop transfer function g of s h of s, assume h of s is equal to 1. So therefore g of s into h of s is equal to 1 by 1 plus ts. So this is the open loop transfer function which is 1 by 1 plus ts. So you can see clearly what is the type of the system, because the type of the system is the number of poles which are going to present at the origin. The number of poles which are going to present at the origin in the open loop transfer function is follow type of the system. The type is equal to 0. And what is the order of the system? The order means characteristic equation is 1 plus g of h of s equal to 0. So if you simplify, we are going to get the value of power of s is equal to 1. So therefore we can say it is a first order system. So type 0 and first order. So if you are going to draw the graph, the magnitude versus the phase angle for this open loop transfer function as a value of omega is varying from 0 to infinity. So you are going to get in this fashion. Just from here to here you are going to get. So in this format we are going to get here. So this point always you have to keep in your mind. So this is a point always, this is the graph that we are going to get here. So now listen carefully. So always this point always you have to keep in your mind. So this is basically the type 0. So this is a type 0. So always remember the shortcut that I am going to write here. So the shortcut to remember I am going to write here. Very simple. So this point always you have to keep in your mind. This is a type 0. This is type 0. This is type 1. This is type 2. This is type 3 system. And then what is the order? Order is like this one. So I am going to write with the other pen so that you can easily able to understand. So this is the order 1. And this is the order 2. And this is the order 3. And this is the order 4. So these things always you have to keep in your mind. So if you see clearly type 0 means starting from here. Order 1 means it will end here. So therefore like this you are going to see the graph. The same thing here. So the system is type 0 and the order is 1 means it will go from here and it will end here. Same thing you can see clearly here. Now let's go for the another transfer function g of s h of s is equal to 1 by 1 plus t1s into 1 plus t2s. So now you can see clearly what the type of the system. Type is I have already told you. The number of poles that are going to present at the origin and the open loop transfer function is for type of system. So type is equal to 0. And what is the order? Order means the highest power in the characteristic equation is follows the order of the system. So 1 plus g of h of s equal to characteristic equation. So if we simplify, we are going to get the highest power is equal to, so order of the system is equal to 2. So now if you want to know what is the polar plot in this plane, then you can simply go for this picture. So you can see clearly that the type is equal to 0. It is going to start from here. and order is equal to 2 means finally it will end here. So it will come like this and finally it will end here. So same thing. It will start from here and it will end here. Same thing. Omega is equal to 0 to omega is equal to infinity. Now let's go for the other transfer function and the open loop transfer function, which is g of h of is equal to 1 by 1 plus t1s into 1 plus t2s into 1 plus t3s. So what is the type of the system? We can say the type of the system is the number of open loop, the number of zeros which are going to present at the origin and the open loop transfer function is called as the type of the system. Here type is equal to 0. And what is the order? Order means the number of the highest power in the characteristic equation is called the order of the system. So characteristic equation is 1 plus g of h of is equal to 0. So if we substitute, we are going to get the highest power is equal to 3. So all of the order of the system is equal to 3. So by seeing this picture, we can draw the polar plot. Type is 0 means it is going to start from here, and order is equal to 3 means it will end here. So it will go like this, it will go like this, and finally it will end here. Same thing. It will start from here, it will end here. So this is the picture you are going to get. So now let's go for the entire system. It is having the open loop transfer function g of h of is equal to 1 by 1 plus t1s into 1 plus t2s into 1 plus t3s into 1 plus t4s. So from this we can say what type of a system. Type of system is the number of poles which are going to present in the origin in the open loop transfer function is called type of a system. So your type is equal to 0. And what is the order? Order means the highest power in the characteristic equation is called as the order of the system. So here the characteristic equation is 1 plus g of h of is equal to 0. Then we are going to get the highest power is 4. So the order of the system is equal to 4. So by seeing this picture, we can draw the polar plot for this open loop transfer function. The type is equal to 0 and order is equal to 4 here means it will start from here, it will go like this, it will go like this, finally it will end here. So same thing we can see here. Type is equal to 0 means it will start from here and finally it will end here. So this is the polar plot we are going to get for this open loop transfer function. Now let's go for the another system. The other system is basically, you can say this is the open loop transfer function g of h of is equal to 1 by s. So now you can say what type of a system? Type of system is the number of open loop, the number of poles which are going to lie in the origin in the open loop transfer function is called type of system. So your type is equal to 1. And what is the order? Order is nothing but the highest power in the characteristic equation is called as the order of the system. So therefore, we can say in simple words that the characteristic equation is 1 plus g of h of is equal to 0. So if you simplify, we are going to get the highest power is 1. So the characteristic, so therefore the order is equal to 1. So now if you want to draw the total part for this open loop transfer function, just see this picture. So we can see what is the type. Type is equal to 1 means it will start from here. Starting point is here, and the order is equal to 1 means it will go here. So therefore it will slowly go in this direction. So it will go in this direction only. It will go in this direction only. So type is going to tell you the starting point and order is going to tell you the final point. So you can say the type is going to tell you the starting point and the order is going to tell you the ending point. So now let's go for the other system, which is the g of h of is equal to 1 by s into 1 plus ts. So now we can say what is the type of the system? Type of system is the number of poles which are going to present at the origin in the open loop transfer function is called as the type of the system. So your type is equal to 1. And what is the order? So the highest power in the characteristic equation is called as the order of the system. So the characteristic equation is 1 plus g of h of is equal to 0. So if you simplify, the highest order is 2. So the highest power is 2. So this is the order of the system is equal to 2. So type is going to tell you the starting point and order is going to tell you the ending point for the polar plot. So if you want to draw the polar plot for the system, this see this picture, the type is equal to 1 and order is equal to 2. So it is going to start from here and it will end up in the order 2. So to start from here and it will go to this point. So therefore this is a polar plot you are going to get here for this one. Now let's go for the entire system. Listen carefully. The other system open loop transfer function is g of h of is equal to 1 by s into 1 plus t1s into 1 plus t2s. So this is the open loop transfer function. So what type of system? Type of system is the number of poles which are going to present in the origin in the open loop transfer function is called the type of the system. So the type is equal to 1. And what is the order of the system is the highest power in the characteristic equation is called the order of the system. And the characteristic equation is 1 plus g of h is equal to 0. So therefore the highest power is nothing but 3. So therefore the order of the system is equal to 3. So now if we want to plot the polar plot for this transfer function, is open transfer function, just see the picture. Type is equal to 1 means here and order is equal to 3 means here. So it will start from here and it will end in the order. So starting point is always type and ending point is always order. So therefore, it will start from here and it will end in here. Now let's go for the another open loop transfer function, which is g of s h of s is equal to 1 by s into 1 plus t1 s into 1 plus t2 s into 1 plus t3 s. So what is the type of the system? Type means we can say the number of poles which are going to lie in the origin for the open loop transfer function is called as the type of the system. So here the type is equal to 1. And what is the order? Means the highest power of the s in the characteristic equation is called as the order of the system. So the characteristic equation is 1 plus g of h of s is equal to 0. So therefore the highest power is equal to 4. So therefore the order of the system is equal to 4. So now if you want to draw the polar plot for this transfer function, for this open loop transfer function, the starting point is always type and the ending point is always the order. So it is going to start from here and it will end here. So this is the thing we are going to see. Starting point is here and ending point is here. Now let's go for the another transfer function, another open loop transfer function, which is g of s is equal to 1 by s square. So type means I've already told you, which is the number of poles which are going to lie in the origin in the open loop transfer function is called as the type of system. Here the type of system is equal to 2. And what is the meaning of order? Means the highest power of the s in the characteristic equation is called as the order of the system. The characteristic equation is 1 plus g of h of s is equal to 0. So therefore, the highest power of the s is equal to 2. So therefore, we can say the order of the system is equal to 2. So if you want to draw the polar plot for this open loop transfer function, the starting point is the type of the system and the final point is the order of the system. So type 2 is here and order is 2 is here. It will go in this direction. So you can see clearly. So it will go like this. It will go like this in a straight forward. In a straight time we are going to get like this. Now let's go for the other open loop transfer function, which is g of h of s is equal to 1 by s square into 1 plus t1 s into 1 plus t2 s. So what's the type of system? The number of poles which are going to lie in the origin in the open loop transfer function is called the type of the system. So here the type of system is equal to. And what is the order of the system? The highest power in the characteristic equation is called as the order of the system. So therefore we can say here, so therefore the order of the system is nothing but for the characteristic equation 1 plus g of h of s is equal to 0. The highest power is 3 here. So we are going to get 1, 2, 3. So 2, 3, 4. Basically we are going to get basically this is something but I think this is s the power of 1. Small correction. This is here s the power of 1 is not s square. So small correction here s the power of 1. So let me do a correction. So this is basically s the power of 1 only. So this is s the power of 1 only. So small correction here we are now taking this one. And this one we are going to neglect. So this one is small correction. So this part is not there. So this part is not there. Only 1 is there. 1 plus t1s. So therefore we can say what is the order of the system? So therefore the order of the system is nothing but for the characteristic equation. The highest power is called the order of the system. So therefore 1 plus g of s h of s is equal to 0. So therefore we are going to get the order is equal to 3. So if you want to draw the polar plot, for this one, then we have the initial point is the type of system and the final point is the order of the system. So type is 2 and the order is 3. So it is going to come in this format. So like this we are going to get the polar plot. Then go for the another system. So then go for the other system, which is the open loop transfer function g of h of s is equal to 1 by s square into 1 plus t1 s into 1 plus t2 s. So for this one we can see clearly, which is the type of system is the number of poles which are going to be present in the origin in the open loop transfer function is for type of the system. Type of system is equal to 2. And what is the order of the system? Means the highest power in the characteristic equation is the order of the system. So the characteristic equation is 1 plus g of h of s is equal to 0. The highest power is nothing but 4 you are going to get. So therefore the order of the system is equal to 4. So now if you want to draw the polar plot for this open loop transfer function, the initial point type of system and the final point is the order of the system. So this is the type 2 and order 4. So here we are going to get like this. So this is the type 2 and order 4. So you are going to get like this. Now let's go for the another system. So now let's go for the another system. Here the open loop transfer function is g of s is equal to g of h of s is equal to 1 by s2. Then the type of the system, the type indicates the number of open loop poles which are present at the origin The number of poles which are going to present in the origin in the open loop transfer function is called as the type of the system. Type of system is equal to 3. And what is the order of the system? The highest power of the S in the characteristic equation is called the order of the system. So therefore we can say, for the characteristic equation 1 plus g of h of is equal to 0, the highest power in the characteristic equation is equal to 3. So therefore the order of the system is equal to 3. So if you want to draw the polar plot for this open loop transfer function, the initial point is the type of system and the final point is the order of the system. So this is a type 3 and order 3 means in a straight line we are going to get like this. So this is a straight line we are going to get, straight line. So from here. So this is all about this one. Now let's go for the final thing. It is the last system, which is the open transfer function g of s h of s is equal to 1 by s square into basically you can say s cube into 1 plus t1s. So s cube into 1 plus t1s. So we can say what a type of system? Type of system is, we can simply say a type of system is the number of poles which are going to present in the origin in the open loop transfer function is called type of the system. Type of system is equal to 3. And what is the order? The highest power of the characteristic equation is called as the order of the system. The characteristic equation is 1 plus g of s h of s is equal to 0. Therefore the highest power is nothing but 4. Therefore the order of the system is equal to 4. So if you want to draw the polar plot for this open loop transfer function, the initial point is always the type of the system and the final point is always the order of the system. So therefore type is 3, order is 4. Type is 3, order is 4 means it will go in this format. So it will come here and it will finally join here. So therefore this is the thing that we are going to get. Type 3 and type order 4. So this is the polar plot that we are going to get. So these are the different types of, So these are the different types of the open loop transfer functions and their corresponding polar plot. So this picture, if you remember this important picture, then you can solve any of the polar plot in a very fraction of seconds. So this picture is very much important. So this picture you always have to keep in your mind. In order to solve these questions in a very fraction of seconds. So this is the, I'm trying to need to remember this picture. So this is a type 0, type 1, type 2, type 3. Again type 4, type 5, type 6, type 7, like that. Order 1, order 2, order 3, order 4, again order 5, order 6, order 7. So this point always you have to keep in your mind. So therefore, we can say, if you remember this picture, you can draw the polar plot of any open loop transfer function in a very fraction of seconds. So now, some important points always you have to keep in your mind. No zeros are included. So if you see clearly, in all these transfer functions examples we have taken, we have not included any of the 0. So no 0 are included and all poles are on the edges of S plane. So in the examples what we have discussed, in all the examples that we have discussed, we have not included any of the 0 and all the poles we have assumed to be lying in the LHS of S plane. So this is a point always you have to keep in mind. So for all the examples that we have studied, we have not included any of the 0 and all the poles are going to lie in the LHS of the S plane. So listen carefully. For these open loop transfer functions that we have taken, there are no zeros for this open loop transfer function and all the poles of this open loop transfer function, they are going to purely lie in the LHS of S plane. So this is the point always you have to keep in your mind. So for all the examples that we have discussed here, for all these open loop transfer functions, we have not included any of the 0 and all the poles of this open loop transfer function, we have assumed to be lying in the LHS of S plane. Then these are the plots that we are going to get here. But with the introduction of the 0, the plot of graph is the same but with a different starting and ending points. So, but with the introduction of the 0, the plot of the graph is same but with the different starting and the ending points. Suppose if you are going to include the 0, then what is going to happen? The plot format is same, but only thing is the initial point and the final point is going to get varied. So the plot of the figure is same. But the only thing is there is a variation. There is a variation in the starting and the final and the ending points. So, but with the introduction of the 0, the plot of the graph, the polar plot of the open loop transfer function is going to remain the same, but it will have the different starting and the ending points. So these are the points always you have to keep in your mind. So therefore, in all the examples that we have discussed for this open loop transfer functions, we have not included any of the 0 in this open loop transfer function and all the open loop poles of this open and all the ports of this open transfer function, purely they are going to lie in the S of S prime. And suppose if you are going to introduce a 0 for this open transfer function, then the plot of the graph is going to remain the same, but with only difference in the starting points as well as the ending points. So this is the important point always you have to keep in your mind. Now we are going to discuss another concept, which is the stability from the polar plots. So based on the polar plots, we have to see whether this is a stable system or unstable system. Just by seeing the polar plot, we have to say whether these are the stable systems or unstable systems. That we need to tell confirmly by just by seeing the polar plots. So that we are going to learn now today. So let me assume this is a polar plot. So this is basically polar plot we are going to get here. So based on this, now we have to comment whether this is a stable or unstable. We need to comment. So this is basically S-plane. So polar plot means we know it is a graph between the magnitude of the open transfer function with respect to the phase angle of the open transfer function. So what is the polar plot? This is a diagram with respect to the magnitude of the open transfer function with respect to the phase angle of the open transfer function when the value of omega is varying from 0 to infinity. So the magnitude of g of the h of s with respect to the magnitude of g of the magnitude of the magnitude of g of h of s with respect to the phase angle of g of h of s when the omega is varying from 0 to infinity. This plot is called as a polar plot. So this is when omega is equal to 0 and this is when omega is equal to infinity. Suppose let me take this as the x. X is nothing but this polar plot is going to cut the real axis at a point. So therefore, this polar plot is going to cut the real axis at a point. Let me assume its value is equal to minus x. Just take the magnitude value, then we are going to get its value is equal to x. And the magnitude plot I am going to consider. So this omega is equal to 0 and this omega is equal to infinity. So now, if the magnitude of the x is less than 1, then what is going to happen? So basically, if the magnitude of the x is less than 1, then what is going to happen? Then what is the thing that we can say? Suppose if this magnitude is less than 1, then what is going to happen? Suppose if you draw a unit circle, then we are going to get like this. It is the unit circle that we are going to get because this value is less than 1. So definitely this value, as this value is less than 1, so definitely it is going to lie, inside the unit circle. So if this is a unit circle, then definitely this unit circle is going to cut the polar plot at this point. So therefore, this magnitude is nothing but this magnitude is equal to 1. As I've already told you, what is the meaning of gain crossover frequency? Gain crossover frequency is the frequency at which the magnitude of the g of s h of s at omega gc is equal to 1. So therefore, this frequency is called as the omega gc. So this frequency is called as the omega gc. Whereas, you know what is the phase crossover frequency? Phase crossover frequency is the frequency at which the phase angle of the g of s h of s at omega pc is equal to minus 1 degree. So this is a frequency. So this is a frequency at which the phase angle of the g of s h of s is nothing but minus 180 degree. So this is called as a phase crossover frequency. So therefore, we can say clearly, as omega is varying from 0 to infinity, as you can say clearly, as omega is varying from 0 to infinity in the increasing order, so definitely omega pc is greater than omega gc. So omega pc is greater than omega gc. So therefore, also simply we can say, so therefore omega gc is less than omega pc also we can say. Then we can, the system is said to be stable. I have already told you, whenever the omega gc is less than omega pc, I have already told the system is said to be stable system. So then, what is the, I have already told you, at the phase crossover frequency, means it is a frequency at which the phase angle of the g of h of s is nothing but minus 1 degree. So therefore, the magnitude of g of s h of s at omega pc is nothing but its magnitude is equal to x. Its magnitude is equal to mod of x. You can take here. Just take the magnitude value, just mod of x. Then what is gain margin? Gain margin is equal to 1 by mod of g of s h of s at omega pc. So you know what is the magnitude of g of h of s at omega pc? It is equal to mod x, so 1 by mod x. Then to see it is a unit place. Suppose gain margin in dB, if you want to figure out, it is equal to 20 log gain margin with the base 10. So gain margin is equal to 1 by mod x. As you can see clearly, as mod x is less than 1, then what is going to happen? 1 by mod x will be greater than 1. So Modulus is less than 1 means 1 by modulus will be greater than 1. So definitely now this log is nothing but positive. So overall value is equal to positive. So overall you are going to get positive. So gain margin in TD is nothing but positive. And what is phase margin? Phase margin is equal to 180 degree plus the phase angle of G of s, H of s at omega GC. So you can see clearly the phase angle at omega GC. The phase angle at omega GC is less than minus 180 degree. So this is the angle, right? So this angle is less than minus 180 degree. So this angle is less than minus 180 degree. So therefore 180 plus this is less than minus 180 degree. So definitely we are going to get the overall. So let me this is minus 150. So 180 minus 150 is nothing but plus angle plus 30. So overall you are going to get the cos angle which is plus positive angle. So therefore the gain margin is positive as well as the phase margin is also positive. Therefore I've already told you whenever the gain margin is positive, phase margin is positive, and the omega GC is less than omega PC. So therefore we can say the system is said to be stable system. So therefore we can say the system is said to be stable system. So this for this condition. So now we will see what happens if it is equal. So let me rub this one. Then we'll be able to understand what I am trying to do. Suppose if the mod x is equal to 1, then what is the analysis? Then what is the analysis that we are going to see here? So now listen carefully. When mod x is equal to 1, then what is going to happen? If mod x is equal to 1 means we can say, if mod x is equal to 1 means simply we can say the unit circle is going to get intersect here. So this is the point we are going to get. So like this you are going to get. So this is the thing that you are going to get. So then a unit circle. So if mod x is equal to 1 means this point is going to intersect the unit circle. If mod x is equal to 1 means this point is going to intersect the unit circle. Then I already told you one important point. What is the meaning of you can say what is the meaning of the gain crossover frequency? The gain crossover frequency is the frequency at which the magnitude of the G of s, H of s is equal to 1. So you can say the gain crossover frequency is the frequency at which the magnitude of the G of s, H of s is equal to 1. So this is the omega GC. So this is the frequency at which we are going to get this is equal to omega GC. And what is the phase crossover frequency? Phase crossover frequency is the frequency at which the phase angle of G of s, H of s is equal to minus 180 degree. Same thing here also you are going to get the minus 180 degree. So omega GC is equal to omega PC. So both are going to be coincide. So omega GC is equal to omega PC. So same thing I have written here. So therefore, whenever the minus is equal to 1, then omega G is equal to omega PC. Then what is the thing I already told you? So what is the then what is the magnitude of the G of s, H of s at omega PC is nothing but it is equal to mod x. Is equal to mod x and its value is equal to 1. Just now we have seen. Then what is the gain margin? Gain margin is equal to 1 by mod of G of H of s at omega PC. So its value is equal to 1. So 1 by 1 is nothing but. So 1 by this value is equal to mod x. And mod x is equal to 1. So 1 by 1 is equal to 1. And the gain margin in dB is equal to 20 log gain margin with the base 10. And the gain margin is equal to 1. I have already told you. So therefore, this value is equal to 1 means definitely you are going to get 0 dB. 0 dB. Then what is the phase margin? Phase margin is equal to 180 degree plus the phase angle of G of H of s at omega GC. So now we can see clearly at omega GC, what is the overall phase angle which is equal to minus 180 degree. So plus 180 minus 180 is nothing but we are going to get 0 degree. So therefore we can say finally gain margin is equal to 0, phase margin is equal to 0, and the gain crossover frequency is equal to phase crossover frequency. So therefore we can say the system is said to be marginally stable. The system is said to be marginally stable. So now let's go for the another case, the last case. Suppose if mod x is greater than 1, then what is going to happen? That we are going to see. So let me drop all these things so that we can easily able to understand. Suppose if mod x is greater than 1, then what is the failures that we are going to get at? If mod x is greater than 1 means it is outside the unit circle. This is outside the unit circle means like this we are going to get. So this is the graph. It's a unit circle we are going to get like this. So now we can say I want to prove what is the gain crossover frequency. Gain crossover frequency is the frequency of which the magnitude of the G of H of s is equal to 1. So this is nothing but this frequency is called the gain crossover frequency. And what's the phase crossover frequency? Phase crossover frequency is the frequency of which the phase angle of G of s, H of s is equal to minus 180 degree. So this is nothing but omega PC. So now you can see clearly as omega is varying from 0 to infinity in this fashion. So definitely omega GC is greater than omega PC. So therefore we can say omega GC is greater than omega PC. Then what is the, you can say clearly, so omega GC is greater than omega PC. Then what is the amount of the G of H of S at omega PC? It is equal to mod X. So you can say at omega PC its value is equal to mod X. Then what is gain margin? Gain margin is equal to 1 by mod of G of H of S at omega PC. So you know its value is equal to mod X. So now what is gain margin in dB is equal to 20 log the base 10 of gain margin. So gain margin is equal to 1 by mod X. See, now listen carefully. Here X is greater than 1. X is greater than 1. So I can write in the under fashion also I can write, which is minus 20 log mod X base 10. So X is greater than 1. So definitely this log is positive. Positive value is equal to negative. So then you are going to get negative value. And the phase margin is equal to 1 degree plus phase angle of G of H of S at omega GC. So you know, now if you see clearly, what is the phase angle at omega GC? This is more than minus 180 degree. It is more than minus 180 degree. So this is a point, right? So this point is more than minus 180. Let me assume this is minus 210. Then what is going to happen? Plus 180 minus 210 is nothing but negative we are going to get. Therefore we are going to get a negative angle. So therefore we can say the gain margin is equal to negative, the phase margin is equal to negative, and omega GC is greater than omega PC. So therefore the system is said to be unstable system. So just by seeing the polar plot, we can comment whether a given system is stable or unstable. So finally, I can give a summary. So listen carefully. Whenever the mod X is less than 1, then what is going to happen? Then what is going to happen is very simple. Whenever the mod X is less than 1, the system is said to be stable system. The system is said to be stable system. System is said to be stable system. Then what is happened? You can say the gain crossover frequency is lesser than the phase crossover frequency, and the gain margin is positive, and the phase margin is also positive. So both are positive. Suppose if mod X is equal to 1, then what is going to happen? The gain margin is equal to 0, and the phase margin is also equal to 0. And the gain crossover frequency is equal to phase crossover frequency, and the system is said to be marginally stable system. Suppose if mod X is greater than 1, then what is going to happen? Then the gain margin and the phase margin both are negative. So both are negative, and omega GC is greater than the omega PC. So these things, and the system is said to be unstable system. So this is the summary I can say. Just by seeing the polar plot, we can comment whether a given system is stable, marginally stable, or unstable. So finally, in simple words, I can say, whenever the polar plot is not enclosing the unit, if it is not enclosing the unity, what is less than 1 is outside, so it is not going to enclose the minus 1, 0. So we can say this polar plot is not going to enclose the minus 1, 0. Then we can say the system is said to be stable. So therefore the gain margin is equal to positive, phase margin is equal to positive, and the gain crossover frequency is lesser than the phase crossover frequency. Whenever the polar plot is going to touch the minus 1, 0, then the gain margin is equal to 0, phase margin is equal to 0, and the gain crossover frequency is equal to phase crossover frequency, and system is said to be marginally stable system. So whenever the polar plot is going to enclose the minus 1, 0, then we can say the gain margin is equal to negative, and the phase margin is equal to negative, and the gain crossover frequency is greater than phase crossover frequency. So therefore the system is said to be unstable system. So finally, a simple words I can say, whenever the polar plot is not going to enclose the minus 1, 0, the system is said to be stable system. So therefore the gain margin is equal to positive, phase margin is equal to positive, and the gain crossover frequency is lesser than the phase crossover frequency. Whenever the polar plot is going to touch the minus 1, 0, then the gain margin is equal to 0, and the phase margin is equal to 0, and the gain crossover frequency is equal to phase crossover frequency, and the system is said to be marginally stable system. Whenever the polar plot is going to enclose the minus 1, 0, then we can say that the gain margin is negative, phase margin is negative, and the gain crossover frequency is greater than phase crossover frequency, and system is said to be unstable system. So this is the thing I can say in a very simple format. So finally, I can say in simple words, whenever the polar plot is not enclosed in the -1, 0 means the system is said to be stable. Whenever the polar plot is going to intersect the -1, 0 means the system is said to be less than stable system. And whenever the polar plot is going to enclose the -1, 0 means we can say the system is said to be unstable system. So this is the thing I can say in the simple words. Now we are going to discuss another concept which is called as the mapping. So this is called as the mapping. Suppose if you take a S-plane, and this is called as the P of S plane. So P of S plane. So basically P of S is basically a function of S. So now let me assume it's value. Suppose let me take a small example. Function of S means I will take here S plus 2. So basically now I am going to draw a small amount of circle like this. Only these points I am going to consider. Only these points which are going to lie on this curve I am going to consider. Only these points which are going to lie on this curve I am going to consider only these points. So I am going to substitute all these points. in this equation. Then definitely I am going to get a real part and the imaginary part, because S is the real part and imaginary part. So if you substitute again you are going to get a real part and imaginary part. So now if I am going to plot all these points, so if you substitute all these points here, you are going to get some complex number. So if you plot all these points on this plane, so let me assume we are going to get in this format. We are going to get. So this is called as a P of S plane. So if you plot all these points, if you keep all these points in this equation, then we are going to get some complex numbers. And if you plot all these points in a P of S plane, then we are going to get in this format. So this is the basic thing I want to explain. So therefore, in simple words, I can say, if P of S is the function of S, for example, S plus 2, and I am going to take the locus of all these points. So if I take all these points, if I am going to substitute in this equation, and finally you are going to get some real part and imaginary part. And if you plot in this plane, then you are going to get a curve like this. The locus of all these points, the curve you are going to get like this. So basically we are mapping from S plane to P of S plane. So this is the concept that we have to understand. So basically we are mapping from S plane to P of S plane through a function. P of S is nothing but function of S. So now this concept we will study some more important thing, which is n is equal to P minus Z. Where n is called as the number of encirclements which are found around the origin in the P of S plane. N is equal to P minus Z, where n is called as the number of encirclements which are found around origin in the P of S plane. It is always positive for the anticlockwise direction. It is negative for the clockwise direction. So what is the meaning of n? N means these kind number of encirclements which are found around origin in the P of S plane, and is a positive for the anticlockwise direction and negative for the clockwise direction. So P is nothing but the number of poles of P of S which are inside the green curve. P indicates that this number of poles of P of S which are going to lie inside the green curve, and Z indicates the number of zeros in the P of S which are lying inside the green curve. So this point always you have to keep in mind. So listen carefully. I will explain some important concept here. So first thing I will explain this one. So suppose for a small example I have already told you basically. Suppose there is a sub locus of these points. I am going to take all these points in my S plane, and I am going to keep all these points in the function of S. Then I am going to get some real part and imaginary part. And if I plot on the P of S plane, let me assume you are going to get in this formula. So I am mapping from S plane to P of S plane, as you can see clearly here. Suppose. So now one more concept now we are going to study here. Listen carefully. Suppose P of S is a function of S space, it will have some, we can say numerator as well as denominator we are going to get. So here we are going to get some numerator as well as denominator we are going to get. So denominator roots are called as the poles and the numerator roots are called as the zeros. So now listen carefully. So I am going to make some curve. I am going to make some green curve. So in this fashion in the S plane I am making some green curve. So in this green curve, there are p number of poles and z number of zeros that are going to present in this green curve of P of S. So basically, we can say numerator roots are called as the zeros and denominator roots are called as the poles. So if I am going to plot all these zeros and the poles in this experiment, we are going to get some figure. So now I am going to draw a figure like this. Inside this figure, we can say, suppose let me assume there are p number of poles and z number of zeros. So inside this graph, let me assume there are p number of poles and z number of zeros of this P of S. Then if you plot all these points, if you keep all these points in this P of S, then if you plot all these points in the P of S, then definitely you are going to get some curve like this. Then it is going to encircle the origin for how many number of times that we need to figure out. So it is going to encircle the origin, this curve, how many times it is going to enclose, that we can figure out with the help of n. N is equal to p minus z, where n is the number of encirclements which are formed around the origin in the P of S plane. This is positive for anti-clockwise direction and negative for the clockwise direction. So P indicates the number of poles of P of S which are inside the green curve, and Z indicates the number of zeros of P of S which are inside the green curve. So this one always you have to keep in mind. So finally, I am going to repeat the concept, listen carefully. Suppose there is a curve I have taken, some curve I have taken in the S plane. So I am going to keep all these points in the function of P of S. Then definitely it will have some real part and imaginary part. And if I plot all these values in this P of S plane, we are going to get some certain curve. So I want to figure out how many times it is going to encircle this origin of this P of S. I want to figure out with the help of this formula, which is equal to n is equal to p minus j. So how to get this value? So basically, listen carefully. So P of S is having basically numerator as well as denominator. So numerator roots are called as zeros and denominator roots are called as poles. So plot all these points in the S plane. So inside this green curve, try to figure out how many number of poles are there, how many number of zeros are there of this P of S. So let me assume there are p number of poles and z number of zeros which are going to present in this green curve. We have figured out. And what is the value of n? N is equal to p minus z. So what is the value of n? Is number of encirclements which are found around the origin in the P of S plane. So number of encirclements which are found around the origin in the P of S plane. Is a positive for the anti-clockwise direction and negative for the clockwise direction. And the P indicates this number of poles of the P of S which are going to lie inside the green curve, and Z indicates this number of zeros of the P of S which are going to lie inside the green curve. So finally I can say n is equal to p minus z, where n indicates the number of encirclements which are found around the origin in the P of S plane. So by this curve, so n indicates the number of encirclements which are found around the origin in the P of S plane, and it is equal to positive for the anti-clockwise direction and negative for the clockwise direction. And P indicates this number of poles of P of S, they are going to lie inside the green curve, and Z indicates this number of zeros of P of S which are going to lie inside the green curve. So this is basically mapping from S plane to P of S plane. So now we will discuss some more important concepts. Another view we are going to discuss, which is, let me take a open loop transfer function g of s h of s is equal to k into s plus or minus z1 by s into s plus or minus p1. Then what is the characteristic equation I am going to assume? The characteristic equation is 1 plus g of s h of s, which is equal to p of s I am going to assume. So this characteristic equation I am going to assume its value, it is equal to p of s I am going to assume. Then what we are going to get? 1 plus g of s h of s. So you know g of h of s, just substitute simplify, we are going to get s into s plus or minus p1 plus k into s plus or minus z1 by s into s plus or minus p1. So this is nothing but p of s. So this is nothing but p of s, p of s plane. This is nothing but p of s equation. So this is the numerator and this is the denominator. So this is the numerator and this is the denominator. So for the p of s. So I've already told you the numerator roots are called as the poles. The numerator roots are called as the zeros, and the denominator roots are called as the poles for the p of s. I've already told you. So this is the numerator and this is the denominator. So these roots are called as zeros and these roots are called as poles. But actually, this is a characteristic equation, right? So this is a characteristic equation, right? So these roots are called as a closed loop, zero, closed loop poles. And what is this one? S into S plus or minus P1. These are basically open loop poles. So you can write like this one. Listen carefully. This is open loop transfer function. K into S plus or minus Z1 by S into S plus or minus P1. So I am going to assume P of S is nothing but characteristic equation. I am going to assume it is 1 plus G of H of S. So you know G of H of S, the substance simplify, we are going to get S into S plus or minus P1 plus K into S plus or minus Z1 by S into S plus or minus P1. So this is basically P of S. This is basically P of S. So this is a numerator and this is a denominator. So numerator roots are called as the zeros and the denominator roots are called as the poles. So same thing, zeros are poles I have written. Now, this is basically a characteristic equation. So therefore, these roots are called as closed loop poles, and this is basically open loop poles. So you can see these are the open loop poles. So these are the open loop poles. So you can write in this form. So now, what I am going to take here, I am going to do the mapping from S plane to P of S plane. So listen carefully. S plane is nothing but I will take all the arches of the S plane I am going to consider. I am going to consider full arches of the S plane I am going to consider. Full arches of the S plane. Total entire arches of the S plane I am going to consider. Then this is a P of S plane. So all these points I am going to keep in the P of S, and then so all these points I am going to keep in the P of S, and then we are going to get the real part and the imaginary part, and then I am going to keep all these points in the P of S plane, and then we are going to get a some type of curve we are going to get. Now what is the formula? I want to find this curve is going to, how many times it is going to enclose the origin I want to figure out. So the formula is n is equal to P minus J, where P is nothing but the number of poles which are going to lie inside this S plane. The number of poles which are going to lie in this axis of S plane. So number of poles in the axis of S plane. So number of poles in the axis of S plane. So poles means we can say these are the poles means which are open loop poles actually. So poles means open loop poles, right? So therefore we can say number of poles or the open loop poles which are going to lie in the arches of S plane. So number of poles are the open loop poles. Here poles means basically open loop poles, right? So number of poles are the open loop poles which are going to lie in the arches of S plane. And what is Z? Z means number of zeros. Number of zeros means we can say it's a closed loop poles. So number of zeros are the number of closed loop poles which are going to lie in the arches of S plane. So therefore we can say here P means number of poles or the open loop poles which are going to present in the arches of S plane, and Z indicates number of zeros or the closed loop poles which are going to lie in the arches of S plane. And what is N? Number of encirclements which are formed around the origin in the P of S plane. So N is equal to positive for anti-clockwise direction and negative for the clockwise direction. So now I already told you for stability what we must have in. So for stability means there should be no closed loop poles in the axis of S plane. Then only because the system is said to be stable. So definitely if you want the system to be stable, then definitely there should be no closed loop poles in the axis of S plane. So Z is nothing but the number of zeros of the closed loop poles in the axis of S plane. So this value should be equal to 0. So Z should be equal to 0. So therefore, if substitute Z is equal to 0, then we are going to get N is equal to P. So this is the condition for the stability. Yes, the number of times, the number of encirclements which are formed around the origin in the P of S plane should be always equal to the number of poles which are going to present in the S plane. Number of poles means open loop poles which are going to present in the S plane. Then only we can say the system is said to be stable. So therefore, for system to be stable, we have to say that the closed loop poles lying in the arcs of S plane should be equal to 0. So therefore, the number of encirclements which are formed around the origin in the P of S plane should be always equal to the number of poles or the open loop poles which are going to present in the arches of the S plane. So these things always you have to keep in your mind. So finally, easily remember the concept, which is basically we are given open loop transfer function G of s h of is equal to k into s plus or minus z1 by s plus or minus p1. So I am going to take the p of s is nothing but characteristic equation I am going to assume. So I am going to assume p of s is nothing but characteristic equation. So we are going to get, which is, so if we substitute this value and if we simplify, we are going to get s into s plus or minus p1 plus k into s plus or minus z1 by s into s plus or minus p1. So this is the, for p of s, this is called as the numerator and this is called as the denominator. So numerator roots are called as the zeros and denominator roots are called as the poles. But actually, this is the characteristic equation. So these are called as the closed loop poles. And this is basically the open loop poles. So you can see that open loop poles. So this is the open loop poles I have written. So basically now I want to map from S plane to P of S plane I want to map. So I want to consider the total artist plane I want to consider. Total artist plane I want to consider. So if we keep all these points in the P of S, then we are going to get some curve in the P of S. So now I want to find this curve, how many times it is going to encircle this origin I want to figure out. So n is equal to p minus j. So what is a p? P means the number of poles. The number of poles of P of S means the number of poles of P of S means the number of poles of the number of poles of P of S means or because the number of open loop poles. The number of open loop poles of the number of poles of P of S which are going to lie in the edges of S plane. And that indicates the number of zeros. The number of zeros of P of S are number of closed loop poles. Number of closed loop poles which are going to lie in the arches of S plane. And the elements, the number of encirclements which are formed around the origin in the P of S plane. So we already told you, for system to be stable, and definitely the closed loop poles lying in the axis of S plane should be always equal to 0 because all the closed loop poles should lie in the axis of S plane. Then we can say the system is equal to stable. So no closed loop poles should lie in the axis of S plane. So definitely there should be equal to 0 in that case because the number of closed loop poles are nothing but number of zeros which are lying in the axis of S plane. It should be always equal to 0. So therefore z is equal to 0. So therefore n is equal to p. You are going to get means the number of times the number of encirclements which are made so the number of encirclements which are formed across the origin in the P of S plane should be always equal to the number of poles or the number of poles of P of S or the number of poles of open loop transfer function. The number of poles of P of S or the number of open loop poles of the open loop transfer function which are going to lie in the axis of S plane. So this number of times we should encircle the origin in the P of S plane in order to make the system to be stable. So this is the concept regarding the other view. Now let's go for the simplified view. Simplified view we are going to see here. So in the simplified view, what we are doing is instead of writing this P of S, we will directly go for a G of H of S itself only. So now listen carefully. Same thing, G of H of S is equal to K into S plus or minus Z1 by S into S plus or minus P1. Same thing we have taken G of H of S. So instead of using this P of S, 1 plus G of H of S, we will directly go from here only. So now this is P of S plane, right? Now we will go for G of H of S plane. Directly this only we are going to assume is equal to P of S. So this one directly we are going to assume P of S. Previously we have assumed 1 plus G of H of S as P of S. But now here we are going to assume this itself as P of S. So we can write either G of H of S plane or P of S plane we are going to assume directly. Then what is the thing that we are going to see? So listen carefully. Now listen carefully. Here. Now we are going to entirely. So I will take the entire S plane, entire arcs of S plane I will take here, entire arcs of S plane I will try to enclose. And I will keep all these points. So I will keep all these points. I will keep all these points in this equation, in this P of S or G of H of S. I will keep here. Then I will get some real part and imaginary part. And I will plot in this P of S or G of H of S plane. Then I will get some type of curve we are going to get. So now I want to figure out this curve. This curve is basically the number of times it is going to enclose the minus 1 comma 0. I want to figure out minus 1 plus j0 or minus 1 comma 0. How many times it is going to enclose I want to figure out. So this is what I want to figure out. How many times it is going to enclose the minus 1 comma 0 or minus 1 plus j0 I want to figure out. So same formula n is equal to p minus j. N is equal to p minus j. N means the number of encirclements which are formed around the minus 1 plus J0 in the G of S H of S plane. So in the G of S H of S plane or P of S plane also you can say here. So you can say N indicates the number of encirclements which are formed around the -1 plus J0 in the G of S H of S plane. Then what is the P? P indicates. So what is the P indicates? So this is a G of H of S plane, that so definitely this is called as the numerator and this is called as the denominator. So numerator roots are called as the zeros and the denominator roots are called as the poles. So basically these are open loop poles and these are the open loop zeros. So these are the open loop poles and these are the open loop zeros. So these are the open loop poles and these are the open loop zeros because it's an open loop transfer function. So these are the open loop poles and these are the open loop zeros. So now we can say, see now what's the value of Z? Z indicates the number of closed loop poles. The number of closed loop poles are the roots of the 1 plus G of H of S in the RHS of S plane. So therefore we can say what's the value of Z? Z indicates the number of closed loop poles or the roots of characteristic equation which are going to lie in the RHS of S plane. And P indicates the number of poles of G of H of S in the RHS of S plane. So this formula always you have to keep in your mind, which is equal to N is equal to P minus Z. N is equal to P minus Z. N indicates the number of encirclements which are formed around the -1 plus J0 in the G of S H of S plane. And Z indicates the number of closed loop poles or the roots of the characteristic equation which are going to lie in the RHS of the S plane. And P indicates the number of poles of the G of S H of S in the RHS of the S plane. So this point always you have to keep in your mind. So N is equal to P minus Z. So we can say P means the number of poles of the G of S H of S which are going to lie in the arches of the S plane, and Z indicates the number of closed loop poles. The number of closed loop poles of the roots of the characteristic equation which are going to lie in the arches of the S plane, and N indicates the number of encirclements which are formed around the -1 plus J0 in the G of S H of S plane. So this one always have to keep in your mind. So therefore finally I can say N is equal to P minus J. Where P indicates the number of open loop poles of the open loop, or we can say the number of poles of the open loop transfer function which are going to lie in the arches of the S plane. So P indicates the number of poles of the open loop transfer function which are going to lie in the arches of S plane, and Z indicates the number of closed loop poles or the roots of the characteristic equation which are going to lie in the arches of S plane, and N indicates the number of encirclements which are formed around the -1 plus J0 in the G of S H of S plane. So this formula always you have to keep in your mind. So therefore we can say finally G of S H of S is equal to K into S plus or minus Z1 by S into S plus or minus V1. So if I'm going to take all this full S plane, I'm going to full arches of S plane and I'll plot in the G of H of S plane. Then the formula is N is equal to P minus Z, where P indicates the number of open loop poles. The number of poles of the G of H of S which are going to lie in the arches of S plane, and Z indicates the number of closed loop poles or the roots of the characteristic equation which are going to lie in the arches of S plane, and N indicates the number of encirclements which are formed around the -1 plus J0 in the G of H of S plane. So these things always you have to keep in your mind. So if you want the system to be stability, then definitely there should be equal to 0. Then only we can say the number of closed loop poles that are lying on the arches of S plane should be equal to 0. So therefore it should be equal to P, means the number of encirclements which are formed around the -1 plus J0 in the G of H of S plane should be always equal to number of poles of the open loop transfer function which are lying in the arches of S plane. Then only we can say the system is said to be stable. So these things always you have to keep in your mind. Now let's go for the other concept, which is a Nyquist plot. Nyquist plot means now is a combination of the polar plots in different regions we have to do. So it is basically a Nyquist plot is nothing but it is a type of polar plot, but it is the extension of the polar plot. It is the extension of the polar plot. So this point always you have to keep in your mind. So Nyquist plot is nothing but it is the extension of the polar plot. So now we'll discuss something more about this one. So listen carefully here always. So always So this is the full S-plane. So full S-plane we are going to consider. The total axis of the S-plane we are going to consider. So we are going to consider in this format. So we are going to consider in this format. So this is basically the path 1. So path 1. And this is the path 2. This is the path 3. And this is the path 4. So total we are going to consider 4 paths. So this is the path 1. This is the path 2. This is the path 3 and path 4. All these paths we are going to map in the G of H of S plane. So listen carefully. We are going to consider the 4 paths. Path 1, path 2, path 3 and path 4. All these 4 paths we are going to match in the G of H of S plane. So I1 minus 1 plus J0, I want to figure out this curve, how many times it is going to enclose. Just now we have seen M is equal to P minus J, where M indicates real number of encirclements which are formed around the minus 1 plus J0 in the G of H of S plane, and Z indicates the number of closed loop poles or the nodes of the characteristic equation, which is 1 plus G of H of S, which are going to lie in the axis of S plane, and P indicates the number of poles of the open loop transfer function which are going to lie in the axis of S plane. So these things I already told you. So in order to map the S1, it is basically simple polar plot, right? In order to map the S1, it is basically simple polar plot. Omega is equal to 0 to omega is equal to infinity. It is basically simple polar plot because omega is equal to 0 to omega is equal to infinity. So it is simply polar plot. So in order to map the S1, it is basically simple polar plot because omega is equal to 0 to omega is equal to infinity. We are going to get the polar plot. So now, in order to map the S2, S2 is nothing but this path. So this path is nothing but we have to put the value of S is equal to limit R tends to infinity R into e to the power of j theta, because S is equal to sigma plus j omega. So if you write in the polar format, it will have some radius as well as some angle. So R into e to the power of j theta, and it is having a radius of infinite. So this R is equal to limit R tends to infinite, and theta value is varying from plus 90 to minus 90. So theta value is varying from plus 90 to minus 90. Then only we can cover this entire path. We are going to cover. So if you want to map the S2, we have to put S is equal to limit R tends to infinity R into e to the power of j theta, and theta is varying from plus pi by 2 to minus pi by 2. So if you want to map the S3, it is a mirror image of the S1. So it is a mirror image of the polar plot. So whatever this polar plot we have drawn, for this one, it is just a mirror image of this one. It is a mirror image of the polar plot. So in order to map the S3, it is a mirror image of the polar plot. So whatever this polar plot we have drawn, just take the mirror image of this one in order to get this one. Now, if you want to map this S4, in order to map this F4, so now the radius is very, very small. So RS tends to 0. And it is varying from minus pi by 2 to plus pi by 2. Therefore, put the value of S is equal to limit R tends to 0, R into e to the power of j theta, and theta is varying from minus pi by 2 to plus pi by 2. So basically, I have already told you, Nyquist plot is basically, it is a extension of the polar plot. So for each and every part, we have to draw the graph in order to get the overall Nyquist plot. So therefore, we can say here we are going to get some Nyquist plot we are going to get. The Nyquist plot is basically, I have taken all these paths and I have did the mapping from S1 to G of S. So I have got some Nyquist plot around this G of H of S, around this minus 1 comma J0. So from this I can get the value of number of encirclements which are formed across this minus 1 plus J0, n is equal to P minus J, where n is the number of encirclements which are formed around the minus 1 plus J0 in the G of H of S plane, and Z indicates the number of closed loop poles or the roots of the characteristic equation 1 plus G of H of S which are going to lie in the axis of S plane, and the P indicates the number of poles of the open loop transfer function which are going to lie in the axis of S plane. So this point always you have to keep in your mind. So whatever this graph that you are going to get, it is called as a Nyquist plot. So simply I can say, in order to map the S1, in order to map the S1, it is basically simply polar plot, because omega is equal to 0 to omega is equal to infinity. Now, in order to map the S2, put the value of S is equal to limit R tends to infinity, R into e to the power of j theta, and theta is varying from plus pi by 2 to minus pi by 2. In order to map the S3, it is a mirror image of this polar plot. And in order to map this S4, limit r tends to put s which is equal to base is equal to limit r tends to 0 r into e to the power of j beta, and beta is varying from minus pi by 2 to plus pi by 2. So if you do all this mapping, of full arches plane in g of h of s, then we are going to get a Nyquist plot. And for this Nyquist plot, if you want to figure out how many number of times this Nyquist plot is going to enclose this minus 1 plus j0 means n is equal to p minus z, where n indicates the number of encirclements which are made by the Nyquist plot around the minus 1 plus j0 in the g of h of s plane. N indicates the number of encirclements which are formed by the Nyquist plot around the minus 1 plus j0 in the g of h of s plane, and z indicates the number of closed loop poles or the roots of the characteristic equation 1 plus g of h of s which are going to lie in the arches of the s plane, and p indicates number of open loop poles of the open loop transfer function, or we can say the number of poles of the open loop transfer function g of h of s which are going to lie in the arches of s plane. So these things always you have to keep in your mind. So this is all the concept behind the Nyquist plot. We are going to discuss another concept which is called as the Bode plot. So this is the Bode plot. So Bode plot is basically have the two graphs. One is the mapped plot and the other is the phase plot. So Bode plot is going to have the two plots. One is the mapped plot and the other is the phase plot. So the mapped plot is nothing but 20 log of mod of g of j omega h of j omega with a base 10. With a base 10 here. Versus log of omega with a base 10. So the graph between the 20 log mod of g of j omega h of j omega with a base 10 versus log of omega with a base 10, that is called as the magnitude plot. So now the phase plot is nothing but the phase angle of g of j omega h of j omega versus log omega with a base 10. So this is the two graphs that we are going to plot in the case of the Bode plot. Here also we need only the open loop transfer function which is g of s h of s. So here also we are going to require the open loop transfer function only which is g of s h of s. So therefore we can say the magnitude plot is going to have the two important plots which are the magnitude plot and the phase plot. So here also we are going to use the open loop transfer function in order to draw the magnitude plot as well as the phase plot. So magnitude plot means 20 log of mod of g of j omega h of j omega with a base 10 versus log of omega with a base 10. Whereas the phase plot is nothing but it's a phase angle of g of j omega h of j omega versus log omega with a base 10. So these are the two important graphs that we are going to draw, and this is called as the Bode plot. So Bode plot is going to have two plots. One is the magnitude plot and the phase plot. So magnitude plot means 20 log of mod of g of j omega h of j omega with a base 10 versus log omega with a base 10. Whereas the phase plot is nothing but it's the phase angle of g of j omega h of j omega versus log omega with a base 10. So this is about the Bode plot. So these two graphs we are going to discuss now in a very detailed manner. Suppose for a system game K, how we are going to draw the Bode plot. So let me take the open loop transfer function g of s h of s. So here basically I have taken g of s only, but we have to assume g h of s is equal to 1. So therefore we can say g of s into h of s is equal to plus or minus k. So by default I am going to assume that is h of s is equal to 1. So therefore we can say g of s into h of s is equal to plus or minus k. I am going to assume. So system gain is nothing but plus or minus k. Then for this one, how to draw the Bode plot. So how to draw the Bode plot that we are going to discuss. So g of s is equal to plus or minus k. Then what is g of j omega h of j omega? Wherever s is there, a plus s by j omega. Then we are going to get plus or minus k only. We are going to, because there is no term s. So definitely always we are going to get the same number which is plus or minus k. And also we are going to add which is plus 0 also we are going to add. So this is basically now it is going to look like a complex number. Then I want to know what is the magnitude. The magnitude of g of j omega h of j omega is equal to under 2 or k whole square plus 0 square which is equal to k you are going to get. So this is nothing but this magnitude part is always going to give you a positive value only you are going to get, because the magnitude part is always going to take the positive value. Then what is 20 log of mod of g of j omega h of j omega with a base 10? It is nothing but simply we can say that the magnitude of the g of j omega h of j omega is equal to k. So we substitute we are going to get 20 log k with a base 10. So this is the value that we are going to get, which is a 20 log k with a base 10. So this is the magnitude. This is the magnitude that we are going to get, that will equal to 20 log mod of g of j omega h of j omega with a base 10 is equal to 20 log k with a base 10 that you are going to get. So this is about the magnitude. Now let's go for the phase angle. So what is the phase angle of g of j omega h of j omega? Suppose if k is a positive, then what we are going to get? We are going to get 0 degree for positive k for all omega. For all omega, irrespective of omega, is always equal to 0 for positive k. Suppose if it is minus k means we can say here we are going to get negative axis. So negative, the point is going to lie on the negative real axis. So what is the phase angle? You are going to get minus 180 degree. So for minus k for all types of omega. So therefore we can say the phase angle of g of j omega h of j omega is equal to 0 degree for the positive k for all type of omega, and is equal to minus 180 degree for minus k for all type of omega. So this is what I am trying to tell you. So therefore we can say the phase angle of g of j omega h of j omega is equal to 0 degree for all positive value of k for all omega, and is equal to minus 180 degree for minus k for all type of omega. So now we know the magnitude, we know the phase angle. So now we are going to draw the border plot. We are going to draw. So I am going to draw only the phase angle part, only the magnitude part I am going to draw. So therefore you can see clearly 20 log of mod of g of j omega h of j omega with a base 10. So you know what is that value? You know it is 20 log 10. 20 log k with a base 10. So you know this value is substitute here, and you are going to get a straight line for all the time. So you are going to get a straight line for all the time, and the base is log omega. So the base is log omega. So this is follows 0 dB. So above is follows the positive dBs, and below is follows the negative dBs. So this is log omega. So this is the graph of the body plot for the g of which of is equal to plus or minus k. So which is 20 log k with a base 10. So this is the magnitude plot that we are going to get here. So these things always you have to keep in your mind. So therefore we can say for a system here k, g of h of is equal to plus or minus k. 20 log mod of g of j omega h of j omega with a base 10 is equal to 20 log k with a base 10. Whereas the phase angle of g of j omega h of j omega is equal to 0 degree for all positive value of k for all value of omega, and is equal to minus 1 degree for minus k for all type of omega. So this is the plot that we are going to get. So this you can see clearly from this picture. So this is a 0 dB. So above is nothing but positive dB, and below is called as the negative dB. So this one you can see clearly from this picture. So this is a magnitude plot, or we can say magnitude plot for the system gain of k. Now we are going to discuss about the integral and the derivative factors. So for the integral and the derivative factors, what is the body plot we are going to see. So g of s into h of s, I already told you, by basically we are going to assume h of s is equal to 1. So this is the default case that we are always going to assume. So therefore we can say g of s into h of s is equal to s the power of plus or minus n. Suppose if you are going to use the positive mix, we can say these are zero terms or derivative terms. If there is negative means we are going to get the integral terms. So therefore we can say positive means we are going to get derivative factors, minus means we are going to get the integral factors. So therefore we can say g of h of s is equal to s the power of plus or minus n. Then what is g of j omega into h of j omega? So wherever s is there, replace h by j omega, we are going to get j omega over the power of plus or minus n. Then I want to find what is the magnitude of the g of j omega, h of j omega I want to figure out. So basically I want to find the magnitude part. So therefore, then basically this power I am going to take the upper road. So therefore, under 2 of 0 square plus omega square over the power of plus or minus n. So therefore we can say the magnitude of g of j omega into h of j omega is equal to under 2 of 0 square plus omega square over the power of plus or minus n. So if you solve this one, what you are going to get? So this 2 is a square and 1 by root 2 are they are going to get cancelled. So finally we are going to get 1 over the power of plus or minus n that you are going to get. So therefore we can say the magnitude of g of j omega h of j omega is equal to under 2 over 0 square plus omega square over the power of plus or minus n. So these 2 and root are going to get cancelled. We are going to get finally omega to the power of plus or minus n that we are going to get. Then what is the 20 log of mod of g of j omega h of j omega with a base 10. So what is this value? So what is this value means we know basically what is the the amount of the g of j omega h of j omega we know, which is equal to omega to the power of plus or minus n. So same thing I have substitute omega to the power of plus or minus n, and here the base is 10. So if this plus or minus n, if it comes to here, then what you are going to get finally? Plus or minus 20 log of omega with the base 10. So this is what that you are going to get. So we can say finally 20 log mod of g of j omega h of j omega with a base 10 is equal to plus or minus 20 n log of omega with a base 10. Log of omega with a base 10. So this is about the magnitude plot. This is about the magnitude. So what is the slope? Slope is nothing but this one. Slope is nothing but this one, which is plus or minus 20 n decibels per decade. So this is called as a slope. It is equal to plus or minus 20 n decibels per decade. So this is about the slope. The slope is equal to plus or minus 20 n decibels per decade. Suppose at omega is equal to 1 radians per second, I want to know what is the value. So if you want to know what is the value, we substitute omega is equal to 1, then what we are going to get 20 log of mod of g of j omega h of j omega with a base 10. So we can substitute here plus or minus 20 10 into log of omega is 1 here. So 1 base 10 is nothing but 0. So 0 into everything is again 0 dB. So this is what we are going to get in terms of dB. So this is about the 0 dB. Then what I am trying to tell you? So what I am trying to tell you is nothing but very simple. So therefore we can say at omega is equal to 1 radians per second, it is going to have the 0 dB, and the slope is either plus or minus 20 n. So plus or minus 20 n. If n is equal to 1, we are going to get plus or minus 20 n decibels per decade. If n is equal to 2, we are going to get plus or minus 4 decibels per decade. Like that we are going to get. So simply suppose if n is equal to positive, then what we can say? If n is equal to positive means plus 1, then what is the slope we are going to get? Then the slope we are going to get is plus 20 decibels per decade we are going to get. Suppose if n is equal to positive and its value is equal to plus 2, then we are going to get 40 decibels per decade. Suppose if you are going to get a negative, so n is equal to minus 1 means here what we are going to get, then we are going to get minus 20 decibels per decade, and n is equal to minus 2. N is equal to minus 2 means here we are going to get, simply we can say minus 40 decibels per decade. So this is the point always you have to keep in mind. So therefore we can say for any positive values we are going to get positive slope, and for any negative values we are going to get negative slope. So this is the point always you have to keep in mind. So you can see clearly from this picture. So for equation we are going to get zeros. It is basically of the power, we can say integral of plus means derivative factors, minus means we are going to get the integral factors. So this point always we have to keep in mind. So therefore the slope is plus or minus 20 n decibels per decade. So for a positive we are going to get positive slope, and for negative we are going to get the negative slope. So this point always you have to keep in mind. So now let's go for the first order factors. So for the first order factors, how we are going to get the Borel plot, this we are going to study in a very detailed manner. It can be either 0 or either it can be 4. It can be either 0 or it can be either 4. So I am going to write in a standard format, which is g of h of is equal to 1 plus e is over the power of plus or minus 1. So this is basically in the standard format. 1 plus e is over the power of plus or minus 1. So plus 1 means we are going to get the 0, minus 1 means we are going to get the 4. So therefore h of s I am going to assume its value is equal to 1, a default case. Then in place of s I have substitute j omega, we are going to get g of j omega into h of j omega is equal to 1 plus, in place of s I have substitute j omega, we are going to get j omega t over the power of plus or minus 1. Then I want to know what is the magnitude part. So magnitude of the g of j omega h of j omega is equal to under root of 1 square plus omega t whole square over the power of plus or minus 1. Then this is what that you are going to get. Then what is the 20 log of mod of g of j omega h of j omega with a base 10. So you want to know this value. So you know basically this value, the mod value substitute, we are going to get 20 log of under root of 1 plus omega t whole square over the power of plus or minus 1 with a base 10 that you are going to get here. So now this plus or minus 1, if I take to the this side, we are going to get finally plus or minus 20 log of under root over 1 plus omega t whole square with the base 10. So this is the exact expression. So this is basically the exact expression. So therefore, 20 log of mod of g of j omega h of j omega with a base 10 is equal to plus or minus 20 log of under root over 1 plus omega t whole square with a base 10. Suppose for low frequencies what we are going to get. So for low frequencies what we are going to get, now we will see. So for low frequencies what we are going to get. For low frequencies means we can say this one is very higher when compared to omega t square. So one is very higher than omega t whole square. So we are going to neglect this omega t whole square. Then you are going to get 1 only. So log of 1 with the base is nothing but 0. So this overall value is always equal to 0 dB for low frequencies. It is approximation. Suppose for higher frequencies means we can say 1 is very less when compared to omega t whole square. So we are going to neglect the value of 1. If we are going to neglect the value of n, then this square and this root are going to get cancelled. We are going to get finally, which is 20 log of mod of j omega h of j omega with a base 10 is equal to plus or minus 20 log of omega t with a base 10 you are going to get. So these are the two things that we are going to get here. So therefore this is for 0 dB for lower frequencies, this is 0 dB, and for higher frequencies this equation is plus or minus 20 log of omega t with a base 10. So now I want to find what is the corner frequency. Corner frequency means these two graphs are going to intersect at a common frequency. So what is that I want to figure out. So corner frequency means it is a frequency at which these two graphs are going to get intersect. So therefore 0 dB is equal to plus or minus 20 into log of omega t with a base 10. So if we solve this one, we are going to get. So therefore this will go to here, we are going to get 10 to the power 0 is equal to 1. So therefore we can say omega t is equal to 1. So omega CF cutoff frequency is equal to 1 by t. So 1 by t. So this is nothing but radians per second. So cutoff frequency is equal to 1 by radians per second. So this is the cutoff frequency. Cutoff frequency is equal to 1 by t radians per second. So therefore we can say below this cutoff frequency the magnitude plot is 0 dB, and above this cutoff frequency the magnitude plot equation is plus or minus 20 log of omega t with the base 10. So listen carefully. Below this cutoff frequency, the magnitude plot equation is 0 dB, and above this cutoff frequency, the magnitude equation is the body plot magnitude equation is plus or minus 20 log of omega t with the base 10. So these things always you have to keep in your mind. So this is basically the approximation. These are the approximate graphs. But if you want to know the exact graph, if you want to know what is the exact value at cutoff frequency, so we can say from this approximation we can say at cutoff frequency what is the exact value dB, the approximate value which is equal to 0 dB. But if you want to know what is the exact value of dB means in this equation substitute the cutoff frequency value which is equal to. So therefore we can say if substitute in place of omega cutoff frequency which is 1 by t, so we are going to get at omega is equal to cutoff frequency which is equal to 1 by t. So if we substitute we are going to get the error is nothing but basically the actual value minus the approximate value. Actual value is this value and the approximate value is 0. So that is follows the error. So therefore is equal to plus or minus 20 log of under root over 1 plus 1 by t into t whole square. So t cancels, we are going to get 1 plus 1 is equal to 2. So under root over 2. So under root over 2 with the base 10 is nothing but we are going to get finally plus or minus 3 dB1 that we are going to get. So therefore 20 log root 2 with a base 10 is equal to plus or minus 3 dB that you are going to get here. So this is the point always you have to keep in your mind. So therefore we can say that we can say error or the exact value. So we can say the error or the exact value that we are going to get which is plus or minus 3 dB in the cutoff frequency. For the approximate value is 0 dB and the exact value is plus or minus 3 dB. So therefore if you take positive means you have to take positive, if you take negative means you have to take negative. So this is all about this concept. So therefore, if you are going to draw the graph, so how it is going to look? Suppose if you are going to draw the magnitude plot, then I already told you I am going to basically show you the rough picture of the magnitude plot. I am going to show you the rough part. So let me assume this is 0 dB. So this is 0 dB. So therefore, at cutoff frequency is equal to 1 by t. Here up to here we are going to get 0 dB. And after this, suppose if it's a place means we are going to get the place 20. So upward for place 20. Suppose if you have taken minus 1 means you have here in this function. So this is the graph. For plus 1 means the graph will be upward, minus 1 means the graph will be downward with minus 12 decibels per decade. So this is the point always you have to keep in your mind. So this is the 10 decibels per decade. So this is the graph that we are going to get. Suppose if you want to know what is the exact graph, exact graph is what we can say, here it is 0 dB only, but here there is a small amount of fluctuation, like this one, this is exact graph for the minus one. Suppose if you want to know for this one, for this one is the graph will be like this one. So here I am going to draw here. So like this, it will be there. So like this, you have to keep in your mind. So this is the graph you are going to get for minus 1, and this is for plus 1. Sorry, this is for plus 1 and this is for the minus 1. So these things always you have to keep in your mind. So plus or minus 3 dB. So for plus means we are going to get, for positive means we are going to get plus 3 dB. So plus 3 dB means it will be upward. It will be upward. So minus plus minus 3 dB. So small correction here. So let me keep here in the picture. So here plus 3 dB. So you are going to get plus 3 dB, right? If you take a positive, we are going to get plus 3 dB. So this is the plus, right? So this is the graph. So therefore it will be plus 3 dB means upward part. So like this it will be. So small correction here. So let me show you the picture. So let me show you the picture, actual picture. So therefore you can easily able to understand the concepts. So I am going to grab this graph so that you can easily able to see what I am trying to tell you. So therefore now, if you see here, I will draw the other pen so that you can easily able to understand. So this is what 0 dB. I have already told you this is basically 0 dB. Suppose for plus 1 is plus 3 dB. So plus 3 dB means upper part, so therefore it will be like this one. So like this one we are going to see. And for minus 1 means minus 3 dB. Minus 3 dB means like this one. So like this one. So this is the graph that you have to keep in your mind. So this is the picture, so always you have to keep in your mind. So this is about the first order factors. Now let's go for the quadratic factors. So quadratic factors means whether you are going to get the two zeros or whether you are going to get the two poles. You are going to get in a quadratic equation. So what is the quadratic factor? The standard format, g of s is equal to s square by omega n square plus 2 zeta s by omega n plus 1. So this is the standard format. This is the standard format. Always you have to keep in this standard format only. Always you have to keep. It is s square by omega n square plus 2 zeta s by omega n plus 1. All the power of plus or minus 1. So this is the standard form. Always you have to keep in your mind. So this is basically the standard form. Always you have to write in this format only. So therefore we can say h of s, I am going to assume its value is always equal to 1. So therefore we can say as h of s value, we have already assumed its value is equal to 1. So g of s and h of value, always we have to write in this standard form for the quadratic, plus power is equal to 2. So g of s, h of s is equal to s square by omega n square plus 2 zeta s by omega n plus 1 to the power of plus or minus 1. Then what is g of j omega, h of j omega? Wherever s is there, s is s by j omega, we are going to get finally, which is 1 minus omega by omega n whole square plus j into 2 zeta omega by omega n to the power of plus or minus 1. So wherever s is there, I have replaced s by j omega. Then I am going to get finally g of j omega, h of j omega is equal to 1 minus omega by omega n whole square plus j into 2 zeta into omega by omega n to the power of plus or minus 1. Then I want to find what is the in dB value. In dB value I want to figure out. So 20 log of mod of g of j omega, h of j omega with a base 10. So basically like this we are going to do now to get in dB format. So plus or minus 20. So you are going to, so you have to keep this value here. If you substitute here this plus or minus 1, it's going to come here. Finally you are going to get plus or minus 20 under root over. So this is basically a small correction here. So basically I have not written the, this is basically g of j omega, but I have not written the magnitude format. So what is the magnitude format? So magnitude of g of j omega, h of j omega is equal to, we can say like this. This is the real part and this is the imaginary part. So 1 minus omega by omega n whole square again plus 2 zeta omega by omega n whole square with a root again to the power of plus or minus 1. So this one I have not written. So see clearly the magnitude of g of j omega, h of j omega is equal to and root over 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square to the power of plus or minus 1. So if you substitute this value here, we are going to get finally plus or minus 20 log of and root over 1 minus omega by omega n whole square plus 2 zeta omega by omega n. Here we have to write here also square. So here also square. So now the base 10. Then I want to do some approximation. So basically at low frequencies I can say, at low frequencies means I can easily say. So therefore at low frequencies what is going to happen? At low frequencies this value is always equal to 0 dB that we are going to get. So therefore we can say at low frequencies means whenever the omega is lesser than, means we can say whenever the omega, low frequencies means whenever the omega is very lesser than natural frequencies, then we can say if this omega is very lesser than omega n, then what is going to happen? So this value is neglected, and this value is also neglected because omega value is very lesser. So this value is tending to 0, this value is also tending to 0. So this value is tending to 0 and this value is also tending to 0 because omega by omega n is very less than 1, because whenever the omega is very lesser than omega n, so omega by omega n is always lesser than 1. So this value is neglected, this value is neglected. So 1 is nothing but 1. So log 1 base 10 is nothing but 0 dB. So you are going to get this value. The approximate value is equal to 0 dB. So 20 log of mod of g omega h of j omega with the base 10 that you are going to get its value is equal to 0 dB. But at a higher frequency means omega is very higher than omega 1 means we can say omega by omega 1 is greater than 1. Then what you are going to do? Then this one we are going to get neglect, right? This one we are going to get neglect. Then if you simplify what we are going to get here, then what we are going to get here, we are going to get, then if you simplify, then what we are going to get simply, this one we are going to get neglect. So therefore if you simplify what we are going to get, omega by omega n to the power of 4 that we are going to get, and here what we are going to get, 2 zeta omega by omega n whole square. So if you simplify, we are going to get, so therefore if you simplify this value, it is approximately equal to omega by omega n only you are going to get. So this value is approximately equal to omega by omega n only we are going to get. So this overall value omega by omega n whole square we are going to get. So if you take here square up and down, what we are going to get plus or minus 40 log of omega by omega n we are going to get here. So this one always you have to keep in your mind. So therefore we can say in simple terms I can say, so basically this one we are going to get neglect, and also this value, so this value also we are going to get neglect. So this value also we are going to get neglect. So finally what we are going to get, omega by omega n to the power of 4 with the root means square we are going to get. So omega by omega n whole square, to square come with it, so it comes outward we are going to get plus or minus 40 log of omega by omega n. So listen carefully, whenever the omega is very higher than omega n, this one we are going to get neglect, and this one also we are going to get neglect. So this one is neglected, this one is also neglected. So only this we are going to get remain. So therefore this is square and root are going to get cancelled. Finally we are going to get omega by omega n whole square we are going to get. If the 2 comes before the log, we are going to get plus or minus 40 log of omega by omega n we are going to get. So 20 log mod of g of j omega h of j omega with a base 10 is equal to plus or minus 40 log of omega by omega n with a base 10 we are going to get, and the slope is plus or minus 4 decimals per decade. So if it is a quadratic equation of 0 means, we are going to get plus 4 decimals per decade. If it is a quadratic equation of whole means, we are going to get minus 4 decimals per decade. So this one always you have to keep in your mind. So therefore we can say, then what is the corner frequency? Corner frequency means it is the frequency at which these two graphs are going to intersect. So therefore corner frequency means it is a frequency at which these two graphs are going to get intersect. So what is the frequency means? 0 dB is equal to 0 dB. So 0 dB. So 0 dB is equal to plus or minus 40 log of base 10 omega by omega n. So if we solve this one, we are going to get omega is equal to omega n only. So therefore the cutoff frequency is equal to omega n. So corner frequency is the frequency at which these two graphs are going to get intersect. So therefore if we simplify, we are going to get the corner frequency is equal to omega n that you are going to get. And what is the exact value at corner frequency I want to figure out, the cutoff frequency I want to figure out. So basically, we always used to say corner frequency. So what is the exact value at corner frequency means in this exact equation, just substitute. In this exact, this is the exact equation, right? So here substitute omega is equal to omega n. Then what we are going to get? Then if you substitute omega is equal to omega n and if you simplify, we are going to get. So we are going to get. So here omega is equal to omega n, right? So here omega n cancels. Here both are going to cancel. So 1 minus 1 is 0. So 0 square is 0. So we are going to get 2 zeta whole square. So root and 2 are going to get cancelled. We are going to get only 2 zeta we are going to get inside. So what is the exact value? The exact value is equal to plus or minus 20 log 2 zeta with the base 10. So basically this exact expression of substitute omega is equal to omega n. So therefore what we are going to get? So this value is equal to 1. So 1 minus 1 is 0. Here also omega n cancels. Only 2 zeta we are going to get. So this 2 and split are going to cancel. Finally we are going to get anything. The exact value is plus or minus 20 log 2 zeta with the base 10 that you are going to get. So if you are going to draw the approximate Bode plot graph, how it is going to look? So here, if you are going to draw the approximate Bode plot graph, then what you are going to get? So let me draw it the another pen so that we can be able to see it. Suppose it is a plus 1. Plus 1 means we can say part of the equation of 0. Then up to omega is equal to cutoff frequency omega into 0 dB. If the plus means we are going to get plus 4 decibels per decay. Plus 40 decibels per decay. Because minus 1 means then we are going to get like this, minus 40 decibels per decay. Always you have to write in the standard format. So this is the solution. So for plus 1 means we are going to get like this above 1, and minus 1 means we are going to get minus 40 decibels per decade. So below the cutoff frequency its value is equal to, its equation is equal to 0 dB, and above cutoff frequency its value is equal to plus or minus 40 log omega by omega at the base 10. So these expressions always you have to keep in your mind. Now we are going to discuss the another concept, which is the Bode plot for the lag heat compensator. So basically we are going to draw the Bode plot for the lag heat compensator we are going to draw. So what is the transfer function of the lag heat compensator? I have already told you, which is f of s is equal to v by a of s is equal to k into 1 plus t1 s into 1 plus t2 s by 1 plus alpha t1 s into 1 plus beta t2 s. I have already told you, in the case of lag heat compensator, alpha is lesser than 1, whereas the beta is greater than 1. So this one I have already told you. So therefore now, suppose if you want to know what are the zeros and poles, I have already told you that zeros are nothing but which is minus 1 by t1 and minus 1 by t2. Whereas the poles are the minus 1 by alpha t1 and minus 1 by beta t2. So I have already told you an important point, which is, so for the lead compensator, so these are the lead compensators. So basically we can say these are the lead compensator 0 and pole, and these are the lag compensator 0 and pole. So if you are going to plot on the S-plane, so how you are going to get look like here? So first thing is you have to draw the lag compensator. So this is the lag compensator and this is the lead compensator. So lag compensator 0. What is the 0 you are going to get? Minus 1 by T2. And the pole is minus 1 by beta T2. So in the case of lag compensator, we can say the pole is near to origin when compared to 0. Similarly, in the case of lead compensator, 0 is closer to origin when compared to pole. So this is nothing but minus 1 by beta T2. And this is minus 1 by T2, and this is minus 1 by T1, and this is minus 1 by alpha T1. So this is a picture. So whenever you are going to go from here, this is a lag compensator and this is a lead compensator. That is the reason it is called as a lag lead compensator, because first you are going to see the lag compensator and then you are going to see the lead compensator. So based on this reason only we say this is the lag lead compensator. So based on this reason only we say this is said to be lag lead compensator, because whenever you are going to move in this direction, the first thing that you are going to encounter is lag compensator, then the lead compensator. So based on this only we can say this is a lag lead compensator. So you can say beta is greater than 1, this value is very lesser. Alpha is less than 1, this value is greater. So this is a plot in your S-plane. So now I am going to replace S by j omega. Then what we are going to get? F of j omega is equal to k into 1 1 plus t1 into j omega into 1 plus t2 into j omega by 1 plus alpha t1 into j omega 1 plus beta t2 j omega. So now if I do the simplification, it will be the same thing. I will take in a very simple format, which is f of j omega is equal to k into 1 plus j t1 omega into 1 plus j t2 omega by 1 plus j alpha t1 omega into 1 plus j beta t2 omega. So this is what I am going to try here. Same thing I have told you. What is the pole zero plot? Pole zero plot I already told you in the S plane. So the zeros are basically we can say minus 1 by t2 minus t1 by t1, and the poles are minus 1 by beta t2 and minus 1 by alpha t1. This one I have already told you. So these are basically belongs to phase-like compensator, and these are belongs to phase-like compensator. So whenever you are moving from this direction, the first thing that you are going to encounter is lag compensator, then the lead compensator. That is the reason it is called as a lag lead compensator. So now I want to know basically what is the phase angle of this one. What is the phase angle of this one? I want to figure out. So phase angle of this one. So phase angle of f of j omega is equal to tan inverse of t omega t1 omega. So we can say tan inverse of omega t1 plus tan inverse of omega t2 minus tan inverse of omega alpha t1 minus tan inverse of omega b2 t2. So these two are positive angles, they are going to get added. These two are also positive angles, they are going to get added, but if it go upward, it will become negative. So this is the overall phase angle, which is tan inverse of omega t1 minus tan inverse of omega alpha t1 plus tan inverse of omega t2 minus tan inverse of omega b2 t2, beta omega b2 t2. So now I am going to draw the body plot. So basically you can say, so first we have to see what are the factors. So what are the corner frequencies, and then we are going to see. So k constant is there. So k is there. So there is no corner frequency for a constant k. So what is the amount of 20 log k base 10? So this one I have already told you. 20 log k base 10. Suppose for this one, which is we can say 1 by, so this one the one we are going to take, which is 1 by 1 plus j omega beta t2. So for this factor, because why it is like this, because you are going to get the pole. The first thing that you are going to encounter is the pole. So I will take the pole, which is 1 by 1 plus j omega beta t2. So what is the cutoff frequency? Cutoff frequency is equal to 1 by the time constant. The time constant is nothing but, we can say, what is the time constant? So time constant is basically beta t2. So beta t2 is the time constant. 1 by 1 plus st. Time constant is basically beta t2. So cutoff frequency is 1 by time constant. So you are going to get, so time constant is beta t2. So cutoff frequency is 1 by time constant is 1 by beta t2. So below this one, the magnitude part is up to 0 dB. Above this one, we are going to get the equation. Because of it is a single pole, we are going to get minus 20 log of basically we can say omega time constant. What is the time constant? It is beta t2. So you know the standard equation. So therefore minus 20 log of omega time constant. Time constant is t2 into beta. So what is the slope here? Minus 2 decimals for pk. Similarly so the next thing is 0 means t2. So this one we are going to encounter. So 1 plus j omega t2. So for this one, what is the cutoff frequency? The cutoff frequency is equal to 1 by time constant. Time constant is t2. So cutoff frequency is equal to 1 by t2. So below this magnitude, the border plot is 0. And after this one, we are going to get the equation which is plus 20 log of omega time constant is t2. So plus 20 decimals per decade. And then the next one is a 0. This one is 1 plus j t1 omega. So 1 plus j omega t1. So what is the time constant? t1. So cutoff frequency is equal to 1 by time constant. So therefore 1 by t1. Below this one, the border plot magnitude is 0 dB. And above this one, the border plot magnitude is, because the 0 is plus 20. So plus 20 log of omega time constant is here t1. So plus 20 decimals per decade. So finally we are going to encounter the pole. So pole is minus this term. 1 by 1 plus j omega alpha t1. So time constant is basically alpha t1. So cutoff frequency is equal to 1 by time constant. So 1 by alpha t1. So below this one, the Bode plot magnitude is 0. And above this one, we are going to get the Bode plot magnitude which is minus 20 log of omega. Time constant is alpha t1. So this is minus 2 decibels per decade. So this is all about this one. So basically, for each and every factor, we have drawn the corresponding magnitude plot we have drawn. So now we have to combine all this one in order to get the overall diagram we have to get. So now, if you see clearly, basically what is the first term? 20 log k, 20 log k base 10, 20 log k base 10. So therefore, this is the 20 log k base 10. Then what we are going to get? We are going to get a minus 2 decibels per decade. So minus 2 decibels per decade. When it is going to get occur? It is going to occur at 1 by beta t2. So at 1 by beta t2, yes, it is going to occur, which is minus 20 decibels per decade. So up to here the 0 dB. So here it is minus 20 decibels per decade. So this is going to get added. So now the next factor is 1 by t2. At 1 by t2, this factor is going to get occur, which is plus 20. So up here it is minus 20. So minus 20 plus 20 is nothing but 0 dB we are going to get. Then the next factor is at 1 by t1. We are going to get this 0. Just plus 20. So 0 plus 20 is equal to again plus 20 decibels per decade. Again at 1 by alpha t1, again we are going to get a pole of minus 20 decibels per decade. So if we have minus 20 here, we are going to get minus 20 plus 20 is that 0 dB. So this is the what that we are going to get. So this is the overall picture that we are going to get. So therefore we can see clearly this is 1 by beta t2, this is 1 by t2, this is 1 by t1, and this is 1 by alpha t1. So therefore you can see 1 by beta t2 is less than 1 by t2 is less than 1 by t1 is less than 1 by alpha t1 in terms of magnitude value. Same picture we have drawn. These are the cutoff frequencies. So at this one, we are going to basically get a pole minus 20. So we are going to get minus 20 here. Here we are going to get a 0. So minus 20 plus 20 is equal to 0 dB. Again here we are going to get a 0. So add plus 20. For this graph, we are going to get again plus 20. Here we are going to get a pole. So add minus 20. We are going to get finally 0 dB per decade. So therefore we can say finally, so this is a 20 log k with a base 10. This is 0 dB. At this point, we are going to get a pole of slope minus 20. So add minus 20 to 0, we are going to get minus 20. And here at this cutoff frequency, we are going to get there, add the 0. So 0 has the plus 20. So add plus 20 to the graph, we are going to get 0 dB. And at this point, we are going to get again 0. So add plus 20 for the graph, we are going to get plus 20 decibels per decade. So for this, we are going to get again pole. So add minus 20 for this graph. For this previous pole, we are going to get again 0 dB. So this is the overall picture that we are going to get. So this is going to look like a band reject filter because these frequencies are passed and these frequencies are passed, but not these frequencies because the gain is not uniform for all frequencies. Here the gain is high, here the gain is high, but here the gain is very less for this type of frequencies. So therefore we say this is said to be band reject filter because the gain is not constant for all the time. So for low frequencies are being passed and high frequencies are passed, but not these frequencies. The frequencies below, the frequencies lying in this range are not passed because of low magnitude. So this is called as a band rejected filter. So this is the, we can say, the Bode plot, or we can say the magnitude plot that we are going to get here. So now, if you want to draw the phase angle plot, so if you are going to draw the phase angle plot, so you are going to get in this fashion. So this is a way that you are going to get. So already told you the cutoff frequencies are 1 by beta t2, 1 by t2, 1 by t1 and 1 by alpha t1. So this one I have already told you. These are the cutoff frequencies. So these cutoff frequencies, so here this is nothing but lag compensator. So here we are going to get the lead compensator. I have already told you. So here lag compensator, here lead compensator. So lag compensator means the phase angle is negative. So that is the reason it is downward. It is downward. Lead compensator means the phase angle is positive. So therefore the graph is above 0 degree. So listen carefully. So this is the reference 0 degree. So this is a lag compensator, right? So lag compensator means we can say the phase angle is negative because the output is going to lag the input. This is a lead compensator. So phase angle is positive. So therefore the output is going to lead the input. The phase angle is positive here. So this is called as the maximum phase shift and this is the maximum phase shift. So this maximum phase shift is going to have a frequency which is omega m1, and this maximum phase shift we are going to get at a particular frequency omega m2. So what is this value? Which is geometric mean of the cutoff frequencies, which are the geometric mean of the cutoff frequency, which is omega m1 is equal to root over 1 by beta t2 into 1 by t2. So if we solve this one, we are going to get the omega m1 is equal to 1 by t2 root over beta, and omega m2 is nothing but it is the geometric mean of the cutoff frequencies, which is root over 1 by t1 into 1 by alpha t1. So if we simplify, we are going to get omega m2 is equal to 1 by t1 and root over alpha. So this is the things always you have to keep in your mind. So therefore, I can easily say in the lag capacitor, the phase angle is negative. So therefore, the output is going to lag the input. In the case of lead capacitor, the phase angle is positive. So output is going to lead the input. So therefore, the maximum phase shift we are going to get at a frequency which is the geometric mean of the cutoff frequencies. So therefore, the geometric mean of the cutoff frequencies is the geometric mean of cutoff frequencies. So at this frequency, we are going to get the maximum phase lag, and at this frequency we are going to get the maximum phase split angle. So at this cutoff frequency we are going to get the maximum phase lag angle, and at this frequency we are going to get the maximum phase split angle. So these things always you have to keep in your mind. So this is about the Bode plot diagram for the lag lead compensator. Now we are going to discuss another concept, which is the characteristics of the lead compensator. So what is the characteristics of the lead compensator that we are going to study in a very detailed manner? So basically, it is going to improve the transient state characteristics of the system, that is, speed of the response of the system. So basically, this point I already told you, the basic thing of the lead compensator is always going to improve the transient state characteristics of the system. That is, it is going to increase the speed of the response, means the rise time is going to get decreased. As the rise time is going to get decreased, we can say the system is going to, the speed of the response is going to get increased whenever the rise time is going to get decreased. So we can say it is going to improve the transient state characteristics of the system, that is, speed of the response of the system is going to get increased, means the rise time is going to get decreased. And it is also going to increase the gain crossover frequency. So omega G is also going to get increases because of this lead compensator. So gain crossover frequency is also going to get increased because of this lead compensator. So always remember the lead compensator. By lead compensator, we are going to improve the transient state characteristics of the system, means the speed of the response is improved means the rise time is going to get decreased, and also it is going to improve the, it is going to also increase the gain crossover frequency. So these two things always you have to keep in your mind. So therefore, you can say the lead compensator, by this we are going to improve the transient state characteristics of the system, means the speed of the response of the system is going to get increased, means the rise time is going to get decreased, and also it is going to increase the gain crossover frequency, means omega GCI is going to get increased. So now we will discuss something more about this one. So listen carefully. What is the transfer function of the lead compensator, which is f of s is equal to v of s by v of s is equal to k into 1 plus ts by 1 plus alpha ts. So this is the standard transfer function of the lead compensator, which is f of s is equal to v of s by vi of s is equal to k into 1 plus ts by 1 plus alpha ts. So now what is the 0? 0 is equal to minus 1 by t, and the pole is equal to minus 1 by alpha t. So this one I have already told you, and alpha value is always lesser than 1. So what is the 0? 0 is equal to minus 1 by t, and the pole is equal to, we can say, minus 1 by alpha t. So alpha value is lesser than 1. So definitely as the denominator is very lesser, so overall value will be very, very higher. So therefore, pole will be very far away from origin when compared to 0. So 0 is somewhat closer to origin when compared to pole in the case of the lead compensator. And I've already told in the case of lead compensator, the output is always going to lead the input. So phase angle should be always equal to positive. So therefore, we can say in the case of lead capacitor, the 0 is near to origin when compared to pole. In the case of this explained. So now I want to basically write the phase angle. Phase angle I want to write of f of j omega. In place of s, I substitute j omega, and I want to know what is the phase angle of f of j omega. I want to figure out which is equal to phi, which is equal to tan inverse of omega t minus tan inverse of alpha omega t. So basically, if this angle goes upward, it will become negative. So therefore, phi is equal to tan inverse of omega t minus tan inverse of omega alpha t. So if you apply the tan on the both sides and if you simplify, finally we are going to get tan alpha is equal to omega t into 1 minus alpha by 1 plus omega t whole square into alpha. So I want to find what is the maximum phase angle I want to figure out. What is the maximum phase angle? This phi m I want to figure out. It is going to occur at the geometric mean of these two cutoff frequencies, which is the geometric mean of these two cutoff frequencies. At this two cutoff frequencies, the geometric mean of these two cutoff frequencies, we are going to get the at this frequency only we are going to get the maximum phase angle. So therefore omega m is equal to under root over, just take the magnitude of this one, which is 1 by t into, just take the magnitude of this one, which is 1 by alpha t. So if you simplify, we are going to get which is 1 by t into under root over alpha. So at this frequency only we are going to get the maximum phase angle. So in place of omega, substitute this value, and if you simplify, we are going to get the value of phi m. So replace phi by phi m and replace omega by omega m. So replace omega m and if you substitute, we are going to get the value of phi m. So if you simplify, what we are going to get, tan phi m we are going to get, which is equal to 1 minus alpha by 2 root alpha we are going to get. So tan phi m is equal to 1 minus alpha by 2 root alpha. So I want to write in terms of the triangle. So this is triangle, is right angle triangle. So what is the tan means basically we can say opposite by adjacent. Opposite is 1 minus alpha and adjacent is 2 root alpha. So you know with the help of Pythagoras theorem, this length square is equal to this length square plus this length square. So if you want this length means under root over 1 minus alpha whole square plus 2 root alpha whole square. So if we simplify, we are going to get this length is nothing but 1 plus alpha and this angle is phi m. So now we can write that sin phi m is nothing but opposite by hypotenuse, which is 1 minus alpha by 1 plus alpha. Cos phi m is nothing but adjacent by hypotenuse, which is 2 root alpha by 1 plus alpha. Or tan phi m is equal to 1 minus alpha by 2 root alpha. You can write anything. But I always choose to remember this is sin phi m is equal to 1 minus alpha by 1 plus alpha. So this triangle always you have to keep in your mind. So right angle triangle and this angle is phi m. So 1 minus alpha, 1 plus alpha, 2 root alpha. So sin phi m is equal to 1 minus alpha by 1 plus alpha. So if you simplify, we are going to, so we can also write in the other equation, this alpha is equal to 1 minus sin phi m by 1 plus sin phi m also. So you don't have to remember this formula. If you simplify, this one we are going to get like this. Means if you know sin phi m, you can get the value of alpha also. If you know the value of alpha, you can get the value of phi m also. So in either way we can get. So sin phi m is equal to 1 minus alpha by 1 plus alpha. So what is phi m? Phi m is called as the maximum phase shift. And what is the unit of omega m? Radians per second. And what is the unit of FM? FM is equal to hertz because omega m is equal to 2 pi FM. So from this we are going to get the value of FM. FM is equal to, the unit is hertz. So these things always you have to keep in your mind. So therefore, the geometric mean of these two cutoff frequencies, we are going to get the maximum phase angle. So basically, see, I've already told you cutoff frequencies means in standard format. So time constant is t. So what is the cutoff frequency here? It is 1 by t, and this is 1 plus s tau. Tau is equal to alpha t. Time constant is alpha t. So the cutoff frequency is 1 by alpha t. So these are the two cutoff frequencies. So between these two cutoff frequencies, take the geometric mean, we are going to get the maximum phase angle. So at maximum frequency, we are going to get the, at this phase angle, we are going to get the maximum phase angle we are going to get. So therefore, either you can take the cutoff frequencies or either using by the roots also, just take the magnitude of these roots also, we are going to get the same thing. So both are same always. So these things always you have to keep in your mind. So therefore, we can say that always remember sin phi m is equal to 1 minus alpha by 1 plus alpha, and we can say that this is the maximum phase angle that you are going to get in the case of lead capacitor. So lead capacitor means always the output is going to lead the input. So always the 0 is closer to origin when compared to pole. So these things always you have to keep in your mind. Now let's go for the another concept, which is the characteristics of the phase lag compensator. So we are going to study the characteristics of the phase lag compensator that we are going to study in a very detailed manner that we are going to study. So what is we can say the characteristics of the phase lag compensator. So basically we can say it is going to improve the steady state response characteristics of a system. That is, it is going to eliminate the steady state error between the input and the output. So I've already told you the phase lag compensator is always going to improve the steady state characteristics of the system. It is going to eliminate the steady state error between the input and the output. So therefore we can say in simple words that with the help of phase-lag capacitor, we are going to improve the steady state response characteristics of the system. Means it is going to eliminate the steady state error between the input and the output. Means the steady state error is going to get decreased with the help of this phase-lag capacitor. So phase-lag capacitor is always going to decrease the steady state error. Means it is going to improve the steady state response characteristics of the system. Means it is going to eliminate the steady state error between the input and the output. So the phase-lag capacitor is going to shift the gain crossover frequency to the lower values where the desired phase margin is acceptable. So in simple words, we can say here the gain crossover frequency is going to get decreased, whereas in the previous case, the gain crossover frequency will increase, but it will decrease, opposite nature. The phase-lag compensator is going to shift the gain crossover frequency to the lower values where the desired phase margin is acceptable. Simply, we can say the gain crossover frequency is going to get increased. And the maximum phase lag occurs at the geometric mean of the two corner frequencies. Same thing, there also the maximum phase lag angle is going to occur at the geometric mean of two corner frequencies. Here also the maximum phase lag is going to occur at the geometric mean of the two corner frequencies. So now we can say what is the transfer function of the phase lag capacitor. F of s is equal to V naught of s by Vi of s is equal to k into 1 plus ts by 1 plus beta ts. So this is the, we can say, the transfer function of the phase lag compensator. So what is the 0? 0 is equal to minus 1 by t, and the pole is equal to minus 1 by beta t, and I already told you beta is greater than 1. So therefore if beta is greater than 1, definitely we can say the pole is closer to origin when compared to 0. So pole is minus 1 by beta t and the 0 is minus 1 by t. So pole is closer to origin when compared to 0. So this is a pole to the plot in the S-plane that we are going to get here. So always if the phase angle is always lag, means here we are going to get the phase angle is negative. So phase angle is always, you are going to get the negative. So therefore the output is always going to lag the input. Output is always going to lag the input. So phase angle is always negative. So now if I want to know what is the phase angle, so replace s by j omega, and I want to know what is the phase angle. So phase angle of j omega is equal to phi is equal to tan inverse of omega t minus tan inverse of omega beta t. So if I apply tan on the both sides, then we are going to get finally tan alpha is equal to omega t into 1 minus beta by 1 plus omega t whole square into beta. So I want to know at what is the maximum phase angle I want to figure out. So what is the maximum phase lag angle I want to figure out? So it is going to occur at the frequency which is the geometry two corner frequencies. So two corner frequencies are 1 by t and 1 by beta t. So this is the geometric mean of these two corner frequencies. We are going to get at this frequency we are going to get the maximum phase lag. So the omega is equal to under root over 1 by t into 1 by beta t. So we simplify, we are going to get 1 by t into under root over beta. And you know the value of omega m. Omega m is equal to 2 pi fm. So omega m unit is radians per second and fm unit is hertz. So if you want phi m, replace phi by phi m and replace omega by omega m. So if you substitute omega m here and if you simplify, we are going to get the value of phi m. So therefore we are going to get tan phi m is nothing but we are going to get 1 minus beta by 2 root beta we are going to get. So we can write, I want to basically write in terms of triangle, the right angle triangle. So 90 degree, this is phi m. So this is opposite and side and this is the distant side. So 1 minus beta, 2 root beta. So what is the hypotenuse? Hypotenuse length is equal to under root over 1 minus beta whole square plus 2 under root of beta whole square. So if we simplify, we are going to get this value is equal to this length is equal to 1 plus beta. So you can write in terms of sine also. Sine phi m is equal to 1 minus beta by 1 plus beta, or you can write cos phi m which is equal to 2 root beta by 1 plus beta. You can write anything. But always you have to remember the sign format is sine phi m is equal to 1 minus beta by 1 plus beta. So if you want to write, this is phi m in terms of beta. If you write in terms of beta in terms of phi m, if you simplify, we are going to get beta is equal to 1 minus sine phi m by 1 plus sine phi m. So this is all about this one. See, I want to tell you, you don't have to remember, just remember this standard format, which is k into 1 plus ts by 1 plus alpha ts. Just remember the standard transfer function for both the phase lag and the phase lag. Same thing you have to remember. So formulas are same. Formulas are same for both the things. Just there I have taken alpha, I have taken beta. Anything which both the formulas are same. But you will know, in the case of phase lag compensator, we can say the 0 is closer to origin when compared to pole. In the case of phase lag compensator, the pole is closer to origin when compared to 0. So these things you have to keep in your mind. So therefore we can say the phase, I've already told you, lead compensator and lag compensator. So in the case of lead compensator, it has more volts. So transit also has more volts. Whereas lag has less volts. So steady state also is having less volts. So therefore, match two things of more volts, match two things of less volts. So phase lag compensator is basically used to input the transient response, whereas a phase lag compensator is used to input the steady state response. So transient response means we can say the rise time is going to get decreased and the gain crossover frequency is going to get increased. Whereas here, the steady state is going to get decreased and the gain crossover frequency is going to get decreased. So these things always you have to keep in mind. So phase lag compensator is basically used to increase it is used to improve the transient response, means decreasing the rise time and increase the gain crossover frequency. Whereas in the case of phase lag compensator, it is going to improve the steady state response characteristics, means it is going to decrease the steady state error and the gain crossover frequency is going to get decreased. So both are vice versa. So these things always you have to keep in your mind. So this is all about the phase lag compensator as well as the phase lag compensator. So now we'll discuss some more important concept, which is the figuring out the gain margin as well as the phase margin from the Bode plot. So how to figure out the gain margin as well as the phase margin from the Bode plot? This concept now we are going to study. So how to basically figure out the gain margin as well as the phase margin from the Bode plot? This concept we are going to study. So I already told you what is a gain margin. Initial formula: gain margin is equal to 1 by mod of G of S into H of S at omega PC. At omega PC, I already told you gain margin formula. So gain margin in dB is nothing but 20 log of gain margin into we can say the basis 10. So gain margin in dB is nothing but 20 log gain margin into base 10. So what is the gain margin? 1 by mod of G of S H of S at omega PC. So if it is a reciprocal, we are going to get gain margin is equal to minus of 20 into log of mod of G S H of mod of G of S into H of S at omega PC in terms of dB. So the unit is basically dB. Here the unit is dB. So this is the K1 in terms of dB and the gain margin is unitless here. So if you see clearly, first thing is this value you have to keep. See, at a phase crossover frequency, try to get the magnitude, which is 20 log of mod of G of S H of S at base 10. Try to get this value. Keep this value here and attach minus to it. So you are going to get the gain margin in dB. So from the magnitude, Bode magnitude plot at phase crossover frequency, just to figure out the magnitude. So for that magnitude, just to keep a front minus, then you are going to get the gain margin in terms of dB. So let's remember, phase crossover frequency is a frequency that is the phase angle of G of S H of S is equal to minus 180 degree. So at that phase crossover frequency, just see the magnitude, plot, magnitude Bode plot. So here we are going to get 20 log mod of G of H of S, mod of G of H of S 10 at omega PC. So for this one, just attach the minus to attach, then we are going to get the gain margin in dB. So therefore, by this way, we are going to get the gain margin in dB just by seeing the Bode plot. So what is the phase margin? Phase margin is equal to 180 degree plus the phase angle of G of S H of S at a gain crossover frequency. So what is the phase margin? Phase margin is equal to 180 degree plus the phase angle of G of S H of S at a gain crossover frequency. So what is the gain crossover frequency? Gain crossover frequency means it is the frequency at which the magnitude of the G of S H of S is equal to 1. Then what is the in terms of dB value, we are going to get 0 because it's a frequency at which we are going to get the magnitude of the G of H of S is equal to 1. So in terms of dB means its value is called 0 dB. So therefore, at 0 dB, in the magnitude plot at 0 dB, just figure out the corner at what frequency we are going to get the 0 dB. Just figure out from the Bode magnitude plot. So we are going to get the gain crossover frequency. So at this gain crossover frequency from the phase angle plot, just get the phase angle. So keep the value and add plus 180, you are going to get the phase margin value that you are going to get. So therefore we can say, finally, in simple words I can say, the phase crossover frequency, it's the frequency at which the phase angle of G of H of S is equal to minus 180 degree. So at that phase crossover frequency, just see the magnitude Bode plot, and that for that value, just attach minus, we are going to get the gain margin in dB. Whereas the gain crossover frequency is a frequency at which the the amount of g of h of is equal to 1 is in terms of dB, its value is equal to 0 dB. So at 0 dB, in the amount to plot, just go for the frequency, that is called the gain crossover frequency. So at the frequency from the phase angle plot, try to get the phase angle and add plus 180, then you are going to get the phase margin. So by this way, just by seeing the Bode plot for the open loop transfer function, we can figure out the gate margin as well as the phase margin very easily. So therefore, this is the concepts always you have to keep in your mind.